Okay, perfect. Let's wait 2 minutes or 1 minute now, and then I'll go going. How's everybody doing? Yeah, thanks for joining me. Appreciate it. Who here knows what morphology is in general? No? Oh, cool. Okay. Yeah. Okay. Yeah. Well, that's the thing I'm trying to kind of use as the example for how we should start to think about these things. So I talk about what it is at the beginning of the presentation. So that's good that nobody's familiar, because then it's not going to be repetitive. And also, you won't know if I'm right or wrong on that topic. So you trust me? That's dangerous. That's dangerous. All right, we'll go ahead and get started. I'm Jared Atkinson. I'm the chief strategist at SpectreOps. And this is the malware morphology workshop. Make sure I could actually change. So just a little bit of my background. I was in the US Air Force, kind of is where I got my start. Hey, guys. And this is a picture of the ops center that I worked in. So it's a secret facility, but they brought in some people to take pictures of it to kind of show it off in the Air Force newsletter or whatever. And so I was able to find it online and share it. So I actually wrote this ASCII stuff up here. Spent a lot of time making everything pretty with those boxes. But I want to start off with kind of a story that illustrates why I think this type of analysis is really important. So when I was in the Air Force, we were doing this exercise called Cyberflag, and it's in Las Vegas, and basically all the different US military services come together, the cyber divisions, and they kind of work on this exercise. And the idea is that they bring in the NSA Red Team and the Air Force Red Team and all these kind of big military red teams, and they'll attack the network, and our responsibility was to be threat hunters and find them, right? And one day, the white cell, which are kind of like the referees, I guess you could say, of the exercise, they came to us and they said, hey, the red team has a golden ticket. What are you guys going to do about it, right? And this was in 2014, and I don't know if you're familiar with golden tickets, but golden tickets was an attack that came out at Black Hat in 2014, and so it was right after it had come out, and we're like, oh, we're going to go find that golden ticket and we're going to take care of it. And then they left, and we all looked at each other and we're like, does anybody know what a golden ticket is? Right. So this is where we were at, right? We had the golden ticket. And that was the moment that we realized that it's like, you can't detect what you don't understand, right? Because where do you even start if you don't know what a golden ticket is? You have no chance, right? And so the idea is that you can't detect what you don't understand, and there's levels of understanding, right? The more thoroughly you understand something, the higher the ceiling is on your ability to actually deal with it, right? And so then that breeds the next question of, how do I start to understand something so that I have the maximal capability of actually trying to detect it? And that's what we're trying to go into in this workshop. So we're going to do an introduction to morphology, like 3 slides just to kind of talk about it. Morphology is, generally speaking, the study of the form and structures of things. So the places where you're going to see it most frequently used are in biology. So the structure of organisms, right? So like anatomy, for instance, we're all probably familiar with anatomy. That's an example. That's a subdiscipline of morphology. And that's how we start to say things are similar or different, right? So you might look at the size of an organism's brain and say that organisms that have similarly sized brains might be similar in how they operate. Or you might look at the fact that we're bipedal, right? We have 2 legs, and like a dog has 4 legs. And so that would be use of morphology. But it's also used in linguistics. And so the structure of words is a study of morphology, right? And so the idea here is that generally speaking, morphology can be used to identify similarities between things, right? So 2 organisms, chimpanzees, for instance, and humans that both walk on 2 legs might have some sort of similarity in their what they call the phylogenetic tree, that their like evolutionary background, as opposed to things that live underwater, right, because they don't have lungs in the same way, they may not be very closely related, right? And so you could say that like we're more different from whales, for instance, than we are from chimpanzees. And you could tell that just by looking at the two different organisms, okay? And so what we're trying to do is figure out how can we look at malware samples morphologically to then evaluate the similarity between the samples, right? So the idea is that the more morphologically different two samples are, the more different they are going to behave, basically, when they're executed, okay? All right, so biologically, you're probably familiar with this picture, right? So there's this idea of how it's called the Linnaeus taxonomy, and that's how we organize species into groups, right? And so, for instance, we're Homo sapiens, right? And like dogs, this is actually wrong. So dogs are a species called Canis familiaris, and then you have wolves, which are Canis lupus. And so that like the way that they start to organize these things together is at the species level, but then there's, for instance, dogs and wolves belong to the same genus, right? And the genus is like one level higher in being abstracted, but it includes both dogs and wolves because they're very similar. And then if you go a level higher, you would have dogs, wolves, and foxes, right? And if you go a level higher, then we're talking about carnivores, right? And so carnivores are going to be dogs, wolves, foxes, lions, but lions are cats, right? So they don't belong to the dog category. And then you have apparently mammals, and I didn't know this, but maybe the big distinction of mammals is that they feed on milk as infants. Who knew that? I mean, I knew that happened. I just didn't know that was the main thing that classified them. And so you have, rats would be included. And then you have, animals that have backbones, so vertebrates, right? And that would include birds, for instance, and so on and so forth, all the way up. And the idea is that the lower down in this structure that you can group two things together, the more similar they are, right? So for instance, you could say a dog and a wolf are more similar than a dog and a lion because the dog and the wolf share the same genus and the dog and the lion share the same order, right? All right. And then you have linguistics, and I'm not even going to attempt to pronounce the French version. I speak Italian, so I know how to say that. But you have this word herba in Latin, and that gets that was the root that influenced the development of many different languages, right? So all the Romance languages are based on Latin. You all probably know that. But every child language of Latin had a slight difference, a different way that they took that word and implemented it, right? So for instance, Italian is erba, right? So they just dropped the H became silent. And in French, from what I understand, the H is silent as well, but you didn't get rid of it, you just kept it around, right? So, and then the E is silent, I guess, I don't know. Yeah, erb, is it erb? Okay, so the idea is that you could start to look at this, and it's actually pretty cool because in linguistics, what they do is they're actually going the opposite direction, right? So they're saying, let's look at all the Romance languages, see how they say certain words, in this case, grass, right? And then they'll be able to link that back to what the kind of root word was in the parent language in Latin. But then you could actually go even further back and start to reconstruct dead languages or lost languages. So there's a language called Proto-Indo-European, which is the language that Latin and German and Russian and a bunch of other languages came from. And nobody has any written record on that. Nobody speaks it. Nobody even knows that it exists, but they know what certain words are based on certain rules and certain trends that they can observe in the existing languages. So one really common trend in languages is that the H sound tends to drop off over time, right? And so you see this in every single one of these languages, the H dropped off. So you have erba in Italian, you have erva. So B's and V's, they have similar sounds. So a B is like a B, it's like a voice or a non-voiced. And then you have a V, which is V, and that's voiced. And they're essentially the same consonant. They just have the way that you push out the air is different, right? And so the idea is that you can actually start to analyze and say which of these words is more similar to the parent. So for instance, erba in Italian is the most similar to Latin herba. But then, for instance, Romanian, which is, according to this, iarba, I don't speak Romanian, so don't judge me. is the most different. It's the one that changed the most from the source. Now, you could then go to other languages. For instance, in German, you have Gras, right? And that's similar to English grass. And in Norwegian, you have Gress. And you're like, okay, well, those all are obviously similar to each other, but they seem different from Herbe, the Latin version, right? And so where did that come from? And then you have Korean, for instance, which I just Googled this. So Jondi, I guess. And that would be even different, right? Because that probably very unlikely shares the same higher order root, right? And so just the idea here is that you can, in biology and linguistics, it's very well established that you could use morphology to start getting an idea for how things work. Now, the interesting thing, like I said, you have this language Proto-Indo-European, and both German, right, and Latin both derive from Proto-Indo-European. Olaf, how do you say grass in Dutch? Gras, yeah, okay. Yep. Okay, there we go. And so what you can find is that all of these words come from, I have no idea how to pronounce this, but gre, maybe. And that's the base word that Latin then changed to herba in some miraculous fashion. And in German, they changed it to gras, right? And so like both those words, even though they appear different on the surface, they have the same parent. And so you could say at a high level, they are relatively similar, as opposed to, say, the Korean version, which is going to be very different and is not related to Proto-Indo-European. Okay, so what does that mean for us? Well, there's two different types of taxonomy. So we had that Linnaeus taxonomy, this one here, and that is what we call like a scientific taxonomy. And that was built based on morphological analysis. So you would look at the structure of these organisms, and some of it is just visual, but then you also have kind of scientific type analysis. And you could develop taxonomies based on that. But you also have what they call folk taxonomies, which are these taxonomies that are essentially cultural or like old school before science was really a thing, right? And so this would be based on like obvious tendencies of things, right? So you could just look at an organism and kind of classify it with things that appear to be similar without doing like really scientific analysis. And so, for instance, one question that might arise is, like bats, for instance, right? Bats, if you just were to look at a bat, it appears to be more similar to birds than to mammals, right? And so it wasn't until people started kind of analyzing bats scientifically that they realized, okay, hey, this is, we're looking at its habits. We're apparently looking at whether or not it's, children come in eggs, or whether they're birthed in different ways. Or I don't know, apparently bats, maybe they feed their young milk, I don't know. But there's different things that they started to look at bats, and they're like, okay, well, that's, even though it appears to be a bird, it's not actually a bird, it's more like a mammal. And so similar thing for whales, right? So you might say that a whale is more similar to a fish than a mammal, but whales are also mammals, right? And so what you find is that the overlap between folk taxonomies and scientific taxonomies are actually quite large. But the problem is on the edges is where you start to get divergence, right? And so that's an interesting thing. One of the ways that this becomes relevant is I think that, for instance, MITRE ATT&CK, the way that they organize different things into techniques, that's more similar to a folk taxonomy, right? And so what you're going to find is that most of the time it's going to be accurate. The classification of things and the groupings of things are going to be very accurate. But sometimes you're going to find, hey, that doesn't really make that much sense, or I don't know how to fit this thing into the existing taxonomy. That's because it's a folk taxonomy, and it's not fully a scientific taxonomy. All right, so there's some fundamental questions that we have to ask. So imagine that you're an attacker and you're trying to laterally move from one machine to another machine, and there's a number of different tools that you can use to do that. So there's a bunch of different techniques you could choose, and maybe you choose to laterally move through a Windows service. And then when you make that decision, there's a bunch of different tools, right? So there's a tool called sc.exe, and you could create a service on a remote machine that way. You could use PowerShell's new service commandlet. You could use a third-party tool called sharpsc to do that. And so the question that you could be asking, one important question is how similar are all of those different tools? So the attacker is asking the question of, do any of these give me an advantage over the defenders if I were to use one versus the others, right? Because from the attacker's perspective, they all create a service, they all get lateral movement, but maybe one does it in a certain way that's going to make it advantageous. And so the question is how similar are they, right? Then there's this idea of techniques in the kind of MITRE ATT&CK kind of idea. So service creation for lateral movement. That would be an example of attack. Credential dumping from LSASS would be a technique. But then there's tools, so sc.exe, sharp sc, but there's this question of, are there, just like we have, species, and we have like the class, right? So imagine that the class is mammal and the species is Canis lupus, right? Are there layers of the taxonomy that exist between the tool and the technique that we don't know about? And the idea that I'm trying to present is that the answer is yes, right? And then, are there degrees of similarity? So just like if two things are the same, right? Who here, if you wanted to look at two different binaries on a computer, two different files, how would you determine that they're the same? Does anybody have an opinion on that? Hash, right? And so hash is like absolute similarity, right? So if you change one bit, then they're not the same anymore. But could you say that there are, when you're talking about things that are different, could you say that there's things that are more different than others? So imagine, like, if I changed one bit, that's still pretty similar, right? But if I changed a gigabyte, right, like that would be very different. And a hash doesn't allow you to evaluate the relative similarity, if that makes sense. It's only absolute similarity. And so we go into that, and so you answered the question right before the next slide, which is perfect. And so then the question is how do we start to evaluate whether things are slightly the same or very different, right? Because if something's very different, then we don't have to worry about that. But if it's a very small change, then it's probably relevant for us to be aware of it, right? And so we started doing things like piecewise or fuzzy hashing. And this is where you hash sections of a file and then you compare them. And it's like if a lot of the sections end up being the same, then we can say, that's mostly the same thing. You also have imp hashing, which we'll talk about the import table in portable executable files later on. But the idea is that like binary files on Windows, they have dependencies on functions that the operating system makes available. And the idea is that if two binaries have the same dependencies, then they're probably doing similar things, right? And so you could look at the import table and hash the contents of the import table and say, if these things are the same, then we could say that these two files are basically the same. Now, those are kind of like two of the ways to start answering the question of like just how different are these things, but there's more questions. So I never do a presentation without having a little philosophy built in, and so this is Plato's theory of forms. Who's familiar with like Plato's cave? Yeah. So Plato's cave was the allegory of the cave was representative of this theory of forms, generally speaking. And so the idea, and this actually has like a object-oriented programming kind of there's a way we could talk about this in the context of object-oriented programming, right? So who here is a programmer? Anybody? I know, Simon, you said you're a developer. Okay. Okay, cool. Well, we'll talk about them both ways. So imagine that everything that you see in the world is what Plato would refer to as a particular, right? So this is a table, right? But it's a unique instance of a table. That's a table. And even though we would say that like this table or maybe these two tables that are connected right here, those are the same table because they maybe like the vendor sells them as under the same SKU or something like that. So they're the same table, but they're not literally the same table, right? The fact that there's two of them tells us they're not literally the same, right? And this table is slightly different than that table, right? Because it's wider than this table. And so but for whatever reason, we're able to classify them under the same category table, right? Even though they're different. And tables come in all kinds of shapes and sizes, but at the same time, we're always able to see, we're able to look at it and immediately say that's a table. And so there's this weird thing that allows us to group things together. And so Plato said that these are particulars, and then the concept, this perfect concept of a table is the form, right? And so that's in this like kind of middle form. So for instance, there would be a form for a house, a form for a horse, a form for a rose, right? And the forms are these perfect representations. This would be similar in object-oriented programming, if you care, to a class, right? So you define a class and then you create instances based on that class. And so the instances would be the particulars. But then there's even higher levels of forms like beauty and justice. They call these the transcendentals, right? So beauty, justice, good, so on and so forth, right? And all the forms are imperfect representations of those higher forms, those beauty and justice and good and all that kind of stuff. And so one of the things that I want you to constantly be thinking about is when you're interacting with tools, like, oh, here's a tool, Mimikatz, right? Mimikatz is a particular. Credential dumping from LSASS is the form. So the technique is the form, and the tool or the malware sample is the particular. And that's kind of a frame of reference that we should keep. And just because two particulars implement the same form doesn't mean that they implement the same form in the same way, right? So if you're talking about tables, you have a rectangular table and you have circular tables, and they implement the same form of a table, but maybe they're not interchangeable in the same way every single time. And so that maybe like if you build an AI model to visually detect tables, you might first build a AI model that only detects rectangular tables, and then you have to kind of go back to the drawing board. And so one of the problems that we need to fight is, let's not build the AI model that only detects rectangular tables. Let's build an AI model that detects the form of tables or any particular table. Then this is kind of the last froofy philosophical idea, but I'm happy to go into that if people like it. So there's this idea called the map is not the territory. Is anybody familiar with that? So I'll just kind of read it and then I'll talk about it. So Alfred Korzybski was a Russian mathematician who wrote a paper in like 1931, and he came up with this idea called the map is not the territory. And he said, a map is not the territory that it represents, right? But if correct, it has a similar structure to the territory, which accounts for its usefulness, right? So it's impossible for a map to fully contain the territory that it covers, because there's an infinite number of amount of detail, right? And so in order for a map to fully represent the thing that it's representing, it would have to, in the perfect amount of detail, it would have to be as big as the territory, and then it would not be useful, right? And so we summarize the territory in the map in a low resolution form, right? But the idea is, in order to be a map, for instance, I'm from California, so I'm going to use California as an example. Fresno is in between Los Angeles and San Francisco, right? And so if you build a map, even though it's not a perfect representation of all the roads or all the territory in California, you would expect that Fresno would be roughly between Los Angeles and San Francisco. If Los Angeles was between Fresno and San Francisco, it'd be a useless map, right? It'd actually be not just useless, it'd probably be negatively useful, right? And so the question is how do we start to build out, as we're building out this taxonomy, the taxonomy is a map, right? So as we start to analyze tools and start to understand the form, we're building a map, and that map is always going to be an imperfect representation of what the techniques that we're interested in are. The question is how do we make sure that it's useful? How do we make sure that we include enough details to make it useful for us? I'm coming from like a detection engineering perspective, but you could also come to it from a number of different perspectives in information security. So, okay. And then there's an idea that a lot of us have this idea of like, as you're working through projects, you might be like, oh yeah, I've seen something that does this attack techniques. We're going to talk about token theft, right? So I've seen something that steals tokens before, and I think it did it kind of in this way. That's valuable knowledge to have, but it's not explicit. So the idea of making a map is that you're making your understanding of something explicit, right? And that's a useful, it's explicit knowledge is significantly more valuable than implicit knowledge. Okay. All right. So I don't know what all your backgrounds are, so I'm trying to kind of give a little bit of an idea of what this might be useful, who this might be useful to. If you're a detection engineer, generally speaking, this is going to really help you understand, as you're building detections, have I scoped out what the problem actually is well? And how do I know that I've actually built a detection that covers that problem in the first place? If you're a red teamer, this helps you to understand the value proposition of one tool versus another tool, and also allows you to help facilitate discussions with defenders about why they may not have detected certain things, right? So it's like, it's one thing for a red team to say, hey, you missed this. It's another thing to say, hey, you missed this because I used this variation or this tool that did it in a certain way that probably would have caused you to miss it for X, Y, and Z reason. if you're a CTI analyst, it helps you to kind of measure the similarity between samples and then get more granular categorization. And then security architects, detection engineers are kind of like, in my opinion, junior security architects. So generally speaking, it's almost always better to create a preventative control than it is to build a detective control, right? So if you could stop bad things from happening, that's better than knowing that bad things happened, because if you know it happened, you still have to respond to it, and there's opportunity for failure there as well. And security architects are going to be the people responsible for implementing these preventative controls, right? And so a lot of these things, if you could detect it, you potentially can prevent it as well, or at least you can think through whether that's possible. Okay, so we're going to start looking at some tools. I think I've already shared the GitHub repository, but feel free to check that out. So it's github.com, Jared C. Atkinson, or Jared Katkinson if you like, and then malware morphology. And we're going to look at token thefts. So everybody knows what token theft is, or? So just in case, token theft, generally speaking, if I'm operating on a machine, right, what I can do, I'm operating as Jared, right? And Olaf, who's in the back, maybe that's his computer. So I'm a red teamer. I've got access to a computer. Olaf is the admin, right? So I'm running under the context of Jared because Jared double clicked on my phishing payload or whatever, right? If Olaf logs in, the operating system creates what they call a logon session. And with every logon session, there's an access token. And that kind of represents Olaf's identity as he moves throughout the computer. And what I can do is I can get access to Olaf's access token, and I can impersonate it. And that would allow me to begin operating in the context of Olaf's user, who might be a domain admin or might be, server admin or something that gives me access to things that I previously did not have access to as the Jared account. And so what we're going to do is we're going to look at 6 different samples that ostensibly do the same thing. They all steal a user's token, right? But they do them in slightly different ways, right? And what we're going to do is we're going to kind of go through a process which allows us to analyze them morphologically, which then allows us to compare and contrast this, how they're different or how they're the same. Okay, so as you're kind of, if you wanted to do this after the class, right, and do this type of analysis, you can just choose any tool and run through this. There are some reasons why certain tools are going to be more complicated than others. The general rule is the first thing you should look at are open source tools versus closed source tools. So you want to look at open source, especially as you're getting going, just to like kind of build up the capability and get used to the process, just because that removes one step of complexity, right? So if you have access to the source code, you don't have to reverse engineer what's going on. And so it's just going to be easier, right? You can just follow through. But just because you have the source code doesn't mean it's easy. I don't know, has anybody looked at the Mimikatz source code ever? Okay, it's a hot mess, and well, if you speak French, it might be easier. I don't know, but it's very, very difficult to follow. And actually, I think I have it pulled up. So let's just look at it. So I'm just going to show us the first sample. We'll dig into this in a second, but we're not even going to look at it to figure out what's going on. But look how simple this is, right? It's one page, 22 lines, easy, right? Here's Mimikatz. So like you can see that there's, am I not sharing? Oh, I am sharing. Okay. I'm not sharing. Okay. Okay. So Mimikatz is significantly more complicated than it has to be, right? So there's easier and harder. And so one thing that you look for is what I call simple versus complex tools, right? So there's tools like out mini dump. There's tools that just do one thing and one thing only, right? And so like you run it and it does the thing that you expect it to do. There's like no command line parameters. You don't have to specify any options. It just does that one thing. And then there's Mimikatz, which will allow you to create a golden ticket, to dump credentials, to steal tokens, to, Kerberoast, to do like 5 trillion different things. And like Mimikatz is going to be harder to analyze as a result of that, because there's a lot of shared code base and there's a bunch of different files and it's more complicated. And so generally speaking, we want open source tools that are simple. And this is just as you're kind of building up that skill set. And then the programming language that the code is written in is going to be important, right? And so I recommend people start with C or C++ tools. And the reason for that, that may seem actually like kind of contradictory, because I would have thought the opposite. So PowerShell, for instance, which is like a programming language I like to write things in, or scripting language, depending on how pedantic you want to be. But the idea with PowerShell or C# or Python or Go or Rust or any of those types of languages is that they have a lot of, they're like managed, or they have a bunch of libraries that like are built in. And so you actually have a bunch of layers of obfuscation between what's actually happening and what the code says, right? And so like in PowerShell, there's a commandlet called get process, right? Get-process. And that does a process listing. It's like a task list, right? It just tells you what processes are running on the system. Well, there's an API function that undergirds get process. But in order to figure that out, you have to go to the .NET reference. You have to go to the PowerShell source code, figure out what, .NET classes is get process calling. Oh, it's calling the system.diagnostics.process class. Okay, well, let me go to the .NET source code and go see what that's doing. Oh, that's calling the int query system information API function. As opposed to in C, it would just say int query system information. You're like, okay, got it. And so C is always going to be kind of like the easiest place to start. And that kind of leads into what does it even mean for something to be a malware sample? So have you ever heard somebody, there's this famous Black Hat booth kind of like advertisement that was it was carbon black, and they said we stop Mimikatz. And that's like one of those things that could mean, it's like it could be interpreted in an infinite number of ways, because like, does Mimikatz mean the like pre-compiled version of Mimikatz that's in the GitHub repo? Or does it mean like any version of Mimikatz, no matter how it's changed? Or does it mean things that do things similar to what Mimikatz does? Like, who knows what it means, right? And that could have been by design, or it could have been through ignorance, who knows? But the idea is that it's not obvious that because you have a tool that it does one thing. And so asking what it does is kind of a weird idea. And so there's kind of these three different levels, I think, of tools. There's standalone tools like that one, that example, new service. What that does is it creates a new service, and there's only one thing it does. There's like complex tools. So like sc.exe would be an example of that. You could create a service, you could delete a service, you can modify a service, you could do all kinds of service type tasks. So there's potentially multiple things that it does. And then you have C2 platforms. So like saying, what does Cobalt Strike do? It's like, well, it could do literally anything, right? And so, so it's just, you get one file. The problem is you get one file, right? So it's like, oh, we have a beacon agent, right? Well, that beacon agent is the agent for Cobalt Strike that's actually a component of a C2 platform that is extensible, and it can do a bunch of different things. And so that's not the same as if you got a file for this out mini dump PowerShell script that only does one thing. And so you have to be kind of cognizant of, am I looking at what the file does? Am I looking at what the module does? Am I looking at what this particular command does? And so we want to break it up into the atomic parts as much as possible. So in the class, we're going to look at, it's all going to be standalone tools. So they're all going to do one thing and one thing only. And so what does the tool do and what does the module or whatever do? Those are going to be synonymous, but that's not always the case. So it's just something to kind of be careful for. So just want to give a little, we're going to start looking at API functions for the Windows operating system. And if you don't know what API functions are, or you don't have any familiarity or experience with them, that's fine. We're going to kind of dig into it, and we're going to start slow. The idea here is that generally speaking, when you're developing code for an operating system, you have to interact with the operating system in some way to get it to do things like show windows, or to, I don't know, authenticate, or do everything that you do, and to create a file, so on and so forth. And in doing so, it's valuable. Like most operating systems will create what they call an API, application programming interface, and that API is going to be your ability. It's going to give you a bunch of pre-compiled capability to interact with the operating system in different ways, right? And it's very useful because a lot of times it hides a lot of complexity, right? So, for instance, if I want to create a file on a computer, I don't want, and like in my application, I don't want to have to understand how the NTFS file system works. And then I don't want to have to understand how the FAT file system works. And I don't want to have to know how to differentiate between NTFS and FAT volumes, for instance, right? That's all a bunch of stuff that is literally irrelevant to me. And so I want it just to work. And so what they did is they created an API function called create file that I call create file, and it does all that magic for me behind the scenes. Okay. All right. And then there's this concept that I call the function chain, which is basically when you create an application, you call different functions, right? And the idea is that the different functions operate in a chain. So in category theory, there's this idea called composability. And the idea is that you have a multi-step process, but each step in the process produces an output that can be used as an input to the next step, right? So like you can't just do step 3. You have to do step 1 and step 2 before you do step 3, because step 1 gets outputs something that's important for step 2, and step 2 outputs something that's important for step 3, or required for step 3. And so what we can do is we can start looking at how these functions are called by applications, especially if we have the source code, and we can start to build out that chain, that relationship between step 1, step 2, step 3, and that becomes valuable for this type of comparison. So going back to our similarity question, right? So if I change 1 bit, right, that means that these things are no longer the same in a literal sense. But would you say if I changed 1,000 bits, that would be more different than if I changed 1 bit? No? Just like excluding the hash. Would you think that generally speaking, if I changed 1,000 bits, it would make more of a difference to the functionality of the program than if I changed 1 bit?
It really depends on what type of.
Okay, that's perfect. Yep. So that's the answer we're going for. So it depends on what the bits do, right? So bits, or usually probably bytes is going to be a more accurate for this conversation, but bytes are symbolic, right? So bytes can be representative of string data. They could be representative of opcodes, right? And they could tell the computer what to do. And so there are certain bytes, right, that are going to be more significant than other bytes, right? And so, like, generally speaking, if I changed 1 byte, it would be less of an impact than if I changed 1,000,000 bytes, almost certainly. But on a byte to byte comparison, it could be drastically different depending on what that byte actually was meant for, right? And so, like, the best example is a NOP instruction, right? So if you've ever thought of a NOP instruction, does anybody know what a NOP does? Yeah. Skip. Yeah. So it does nothing, right? And so that's as low significance as you possibly can have, as opposed to, say, a call instruction, which calls an entire subroutine. So it's like 2 bytes or 3 bytes that represent a whole subset of other bytes, right? And so changing a call instruction, you could say, would be more significant than changing a NOP. Okay. And so a call instruction is essentially a function call. And the most significant version of function calls are APIs, like operating system APIs. And so that's kind of where we're going with this, right? So it's like if you change 1 bit, you make it different, but then, depending on which bit you change, certain bits could be more important than other bits. And so what would be like kind of the most significant change you can make on a kind of bit or a few byte perspective? Well, that would be function calls. And so let's go look at the function calls and see what's going on. Okay. So this is the source code I just showed you, right? So this is the first sample, and it's available on the GitHub. And we, just for time savings, we kind of made it extremely simple. There'd probably be more in real life. There would be like error handling and things like that. But these blue parts are going to be function calls. So not to insult anybody's intelligence, but can people tell me what the names of the functions that are being called are in order? The first one. Open process. Yep. Next one. Open process token, duplicate token, set thread token, close handle, close handle, close handle, right? So that's what it is. So we could build this function chain, and we can say, hey, here's our function chain. You call open process, and the output of open process is this H process variable. And you see that H process variable is used as an input to open process token, right? And then open process token, the output is actually this H token here. And you see that that's being used as an input to duplicate token, right? And then duplicate token outputs H duplicate. And then H duplicate is passed in as a input parameter to set thread token, right? And so you can see that there's this relationship to where you can't call set thread token until you've called duplicate token. You can't call duplicate token until you've called open process token, and so on and so forth, right? So that's that composability thing, right? You can't just call these in whatever order you want. And then you see close handle closes the H duplicate, close handle closes the H token, right? And close handle closes H process. And so there's a little bit more variability in the ordering when we get to the close handles part, right? Because you could close these in whatever order you want, and it's not like this isn't necessarily dependent on, well, like this one, which is the last one, is not dependent upon set thread token. It's actually only dependent upon open process, right? And so there's a little bit of like kind of ordering there that can be there. Now, this is a PowerShell script, and I know that we said don't look at PowerShell, but I actually like kind of cheated and simplified it a little bit so that it you don't have all that redirection in .NET and PowerShell and all that kind of stuff. And so can people tell me kind of what you see with this one? What's the first function call that you see? Open process, right? It's the same, right? So, but we could say that 100% sample 1 and sample 2 are different. They would have different hashes because one's written in C, one's written in C++. So they like, or in PowerShell. And so they're just literally different. And you have things like, for instance, the process ID is being passed in as process ID here, but here it's called PID, right? And then it's called, let's see, H process, H token, H dupe token instead of H duplicate, right? So there's just some like small differences, but those are not important differences, right? And so what we could do is we could build the function chain again. And what we find is that, as you mentioned, the function chain is exactly the same, right? And so now what we could do is we can say that these are literally different, but they are functionally equivalent, right? And so the idea here is that they're different tools written in different programming languages, but they call the same functions. And so what we could say is that the differences between these must be only in the bits that are least significant, right? The most significant bits are all the same. The least significant bits are the things where changes are happening, okay? And so this means that if, for instance, I build a detection looking for set thread token, it would work on this one and it would work on this one because they're the same. And so this is always an interesting use case, right? Because it's two particulars, right? Two instances that are different. But if you build a detection and you could detect, these are mislabeled. This should say sample 1 and sample 2 here. But anyway, if I could detect sample 1 with a detection rule, but I can't detect sample 2, what happened, right? What does that mean? Does that indicate anything to me? Yeah, better detection, right? So what I'm going for is that generally will be an indicator that you have a signature, like a tool, a particular, like an instance specific signature, right? And like this is the easiest type of situation for you to expand your detection and say like, hey, these two things are doing literally the same thing. Why can I detect one but not the other? The most extreme example of that would be my detection depends on the hash of the file, right? So I'm not resilient to any change. The idea is we want to make our detections as resilient to as large of a change as we possibly can, right? And this is a relatively small change, and so we should be resilient to it. So there was, is anybody around when PowerShell was like the real hot thing in like red teaming and attackers? And so then, man, when was this? 2018 maybe. Microsoft came out with a blog post called "PowerShell Loves the Blue Team," and they came out with all the like PowerShell login and script block login and transcript login and all that kind of stuff. And then all the attackers would change all their tools from PowerShell to C#. And I don't know if people are familiar, but PowerShell and C# are both based on .NET. So changing your PowerShell code to C# is like, it's literally the same thing. Like, let's look at I'm going to share my entire screen so that for the recording. So give me a sec just to kind of get that going here. Yeah. All right, so I'm just going to show this real quick. Okay, so there's this, out mini dump. Okay, so we have this tool out mini dump, which I talked about a second ago, and then we have sharp dump. Okay, and so out mini dump is this tool written by Matt Graber, who's now at Red Canary. And what this does is it allows you to create a crash dump for any process, right? And that crash dump, like the reason why they do that as attackers is that you could crash dump LSASS, and then if you crash dump LSASS, you can then find passwords basically in there, right? But out mini dump is written in PowerShell, right? And so here's what it looks like. So you have mini dump write. You call this function mini dump write dump, and you execute it, and you get all this stuff, right? Okay, but then when PowerShell kind of fell out of vogue because now there was a lot more telemetry and a lot more visibility into what PowerShell was doing, another colleague of mine named Will Schroeder, or Harmjoy, he wrote this tool called Sharp Dump, and he literally says Sharp Dump is a C# port. Port just means I rewrote it in a different language of PowerShell's out mini dump functionality, right? And so if we go into the source code, program.cs, let's see. Here it is, mini dump, write dump. So they file stream, I didn't point that part out, but in out mini dump, they create a file, right, using this system.io.filestream class. He also does that here, so file stream. And then they call mini dump, write dump. And so we should be asking serious questions if this change from PowerShell to C#, where all they did was change the language. If that causes our detections to fail, we should be asking serious questions about why that is, right? And we should be very critical of our detections at that point. Okay, so morphology, as we talked about, is kind of popular with biology. That's where it kind of came about. So what I like to do is kind of assign each sample an animal, right? And so in this case, I have an Australian Shepherd at home. This is why I chose that breed of dog. But this sample 1 is going to be represented by this very happy looking Australian Shepherd. But sample 2, which has the same, it's literally different, right? But it's functionally equivalent, is also an Australian Shepherd. It just is a different one, right? And so like one's a little bit more brown, the other one's a little bit more black, but generally speaking, they're the same dog breed, right? And when you think about dog breeds, for instance, or you have these different levels of analysis, right? So a dog breed, if I know that your dog is an Australian Shepherd, I have a certain level of expectations of how that dog's going to act, right? Shepherds herd things, right? They're very energetic. They could jump high. There's certain things that you know about them. But if I just told you I have a dog, right? There's a different level of expectation that's going to be more generic, right? Because dog represents both Chihuahuas and Great Danes, right? So there's a wide range of variation. And so I just know that dogs generally are playful. Maybe if they get angry, they bark. I have some ideas about what to expect, but it's not as specific as Australian Shepherd. And then if I told you, hey, I have a mammal, right? That would give you, like, you would be like, what the hell? Like, that's the weirdest thing that anybody's ever said to me. Nobody ever talks at that level, right? But that would also be an technically accurate statement to make, right? But you would have no, like, it could be a cat, it could be a brown bear. Like, you have no idea what I have at my house. It could be kids. Yeah. Yeah. The worst of all. Yeah. The most terrorizing. Okay. So what we have, do people, I don't know, do people actually want to do labs, or is it fine to just, the labs are available, you can go through and look at them. It's probably, I think it's better if we just kind of do it as a group. And this one is particularly kind of simple, so I don't want to be insulting. But here's a third tool, right? Sample 3. So sample 3 is potentially doing something different. Does anybody see the difference in sample 3 from what you saw in sample 1 and 2? It's also written in C. So sample 1 was written in C, sample 2 was in PowerShell. This is again written in C. So it should be most similar to sample 1, but there's some major differences. You said what? Okay, so it's not cloning the token. So that was the duplicate token call. And then do you notice that here we call set thread token, which is one function? And here we call impersonate logged on user, which is just a different function. And the problem is I have no idea how different that is, right? But the one thing that Olaf pointed out is that it's not calling duplicate token. And so it's like, why does impersonate logged on user not have to duplicate the token? Why does it just get to use a normal token? So we could build the function chain. I'm going to take a drink of water real quick. And I never have like good chances to I don't know how to pause gracefully and drink water. It's a weird thing. Okay, so we have another function chain. And if we again compare now the labels are correct, the function chains of sample 1 and sample 2, which are the same. And so the cool thing about things being the same at one level of analysis, so you have the literal level of analysis, which is the hash, right? And they're different at the hash level. But if we're talking at the function level, which is just a level of abstraction higher, I could ignore all the differences and I could just treat them as if they're the same. And so now I'm only using one function chain, right? This one with the smiley Australian Shepherd. I'm using that to represent both samples 1 and 2. We actually don't even have to talk about the differences between sample and 1. We don't have to talk about sample 2 ever again because it's the same at the functional level of analysis, right? But now what we're doing is we're saying, hey, this is sample 3 and it's functionally different, right? We could build the function chains and see immediately that they're not the same. And so what is that if we were to do some morphological analysis? Okay. All right. So this is where we get into this idea called the function call stack. And this is where we have to get a little more technical. But the way that the function call stack works is when I call a function, so create file, right? In this example, I'm calling create file, and there's actually this whole set of abstraction underneath, right? So I call create file, and then there's a bunch of calls that happen subsequently, right? And so here we see this is create file, and create file is implemented in a DLL called kernel32.dll. And what that does is that calls another function called create file. So that's what this pink thing down here represents. And so I talked about import hashing earlier as just a way to try to see similarity. And so every portable executable, that's like an exe file, a .sys file, so system driver, or a .dll file, is going to have it has lots of things, but two of the things that are worth highlighting are the exports table and the imports table. So I talked about those APIs, right? The exports table represents functions that one binary is making available for everybody else. So this is very common in DLLs, right? So DLLs, the whole point is that they have their shared libraries, they share functionality. And the way that they share that is through functions which they export. And so you could load a DLL into a disassembler or into portable executable file parsing tools, and you would be able to look at the exports table. And in this case, we're looking at kernel32.dll, and we would see that create file W is exported. But we also, I didn't even know that this existed, but there's this LZ create file W that's also exported. And so that's a different way to create a file that's that may be similar and may be completely different. I don't know, but we could look at that and see what's going on there. But then you also have the import table, which is basically this table that says, hey, I'm using functions that are shared by other libraries, and here's where my dependencies are, right? So it's telling you about dependencies. And so when we see this pink one right here, so this is, if we were to just double click, this is the export table, right? If we just double clicked on create file W, it would take us here, right? And then we start to look at it, and then it's like, hey, I have an import, I have a dependency on some other DLL basically, and I'm requesting this create file. So then we go to the imports table and we see, hey, we're importing that from something called API-ms-win-core-file-L1-1-0. Just rolls off the tongue, right? So it's just very easy to say. This is something called an API set, which is essentially this mechanism for as Microsoft extended the different types of operating systems. So they have like server core, but they also have like HoloLens and Xbox, and there's a bunch of different operating systems that will sometimes have the same DLLs and same architecture, but sometimes won't. What they had to do is they added this like extra layer of redirection that allowed it to do checks to make sure that when an application requests something, that they knew where it was going to be, because it's not that like the location of a certain file on HoloLens might not be the same place as on Windows. And so they needed a way to be able to do that lookup. And so there's this PowerShell module called NT Object Manager, which it's at least in the workshop description that says that that's something that we're going to use. But it has a function called get-nt API set. So this was written by James Forshaw at Google Project Zero. And what that does is it allows you to specify the API set, and then it will tell you, hey, if somebody refers to this, that API set on this machine is located in this DLL. It redirects to this DLL. And so it's kernel-based.dll. So we were in kernel32.dll. Now we're in kernel-based.dll. And you can't see it in the class because this thing's in the way. But we're kind of building this vertical chain now. So we have create file in kernel32. We have this API set. We have create file W in kernel-based.dll. And we kind of keep going, right? So then we look at create file in kernel base, and we see that it calls this function called create file internal, right? And then we look at that, and that calls nt create file, which we look up as it's in ntdll.dll. And then that makes something called a syscall. Does anybody know what a syscall is? A syscall is basically a transition from user mode to kernel mode, right? And so when you make a syscall, what you do, so here's the syscall instruction. So just like you have nop instructions, you have move instructions, test instructions, jump instructions, you also have syscall instructions. And that's telling the processor, I want to transition from user mode to kernel mode, right? But then it's like, okay, well, where do I go in kernel mode? Well, there's this table that's a lookup table. And what it is it's based on certain numbers, which are indexes in the table. And in this case, it's saying, I want to go to offset 55, or the 55th entry in that table. And that happens to be a function in the kernel called nt create file. So that's what's happening. And what ends up happening is we transition from create file W in kernel32 all the way down to this syscall called nt create file. And that's in the kernel, right? And so the interesting thing is, has anybody heard of like direct syscalls at all? There's this, probably the most famous tool is a tool called Dumpert, which is a LSASS dumping tool, and written by guys at Outflank in the Netherlands. And what that does is it basically, instead of calling the equivalent of create file W from kernel32, it calls nt create file. And the reason why they do that is some EDRs or some security tools are focused on looking for this, but all of these do the same thing, right? Because if I call this, then I call this. Like by calling this, you are telling the computer to call this, to call this, to call this, so on and all the way down the stack. And so what they found is, well, we could just skip the majority of the stack and go to the very bottom and make the direct syscall. And that allows us to evade any naive EDRs or security products that are focused really high up in the stack, right? And that was really popular like a year or 2 years ago. Most good EDR vendors have kind of like figured that out, and that's not a big problem anymore, but it's still something that we have to be aware of, right? So that means that as an attacker, if I wanted to create a file, I could call any of these functions, right? They're all equivalent, okay? And so what we would do is do a lab, but I'll just kind of, if I could find, there we go. What we could do is we could do a lab. And so I'm going to look at set thread token just to kind of give us a start on this. And so I'm just going to go into Windows System 32 here and set thread token just to kind of show you how this works. So Microsoft has documentation for most API functions. So here's the documentation for set thread token. And what you could do, it tells you this is what it gets used for, right? It tells you these are the parameters. This is kind of like how you would call set thread token. And then this means that there's a parameter called the thread parameter, and then there's a parameter called the token parameter. And then it tells you, hey, for the thread parameter, that's going to be a pointer to a handle to a thread, but it could be null. If it's null, then we're just going to assign the impersonation token to the calling thread. And so when I run code, if I want to impersonate myself, then I would leave that null. And then the token is going to be a handle to an impersonation token, right? Okay. And then we can scroll down to the bottom and it will tell us where that function is being implemented. So ADV API 32.dll. So we could go into our computer and we're in System 32. and we could look up ADV API 32, and we could just drag and drop that into IDA. And that's going to get parsed. And this is what we end up with. You'll see right now it's not super pretty. It's still working. One of the kind of tricks is that you'll see this number kind of keep getting bigger, and then it will stop and then show you what they call the graph view. So this is just kind of the way to look at it. I remember we talked about the import and export table. IDA kind of makes that nice and pretty for us. And so we can literally just come over here, click on exports, and now we're looking at the export table. So just to give you an idea of these like ADV API 32 or kernel 32, the amount of functions that they export, it's a lot, right? So there's a lot going on. And some of them have really great and creative names like system functions 007, you know? I don't know. I wanted to make a GoldenEye reference, but I don't know how it will land. So I'm a little self-conscious, but maybe that function, you know, gives it a little bit more time before it blows up the gas tanks. You know what I mean? Brian, I hope you know that reference.
Yes.
Okay. Or maybe that was 006.
Yeah. Right.
Okay. Come on, Brian. Brian, we got to be a little faster. Brian and I used to work together, so I feel comfortable giving him crap. And he just walked in, so. Okay, so what we're doing is we can just kind of search for set thread token. Okay, and here we are. We just double click on it, and it looks like it's really complicated, right? So it's literally has one instruction, and it jumps into this IMP, which stands for import. So telling us to go look at the import table into a function that's also called set thread token, which can be confusing when you first get started. It's like set thread token calls set thread token, but it's not the same one. So we go to the imports table, and we can do the same thing. Just search for set thread token, and we see that it's implemented by this MS or API MS Win Core process threads L112. And so we could open up PowerShell. Okay. I'm just gonna. I'm pretty good at remembering these, but it's still, sometimes it's better just to have it there so I could read it. And we're going to run James Forshaw's get int API set. And we're going to specify the name, which is API MS Win Core Process Threads L1-1-2. And then there's a little trick that we'll kind of run into later, where you want to expand the host properties. So did I do something wrong there?
You would just try to do both then.
Oh, okay. Gotcha. Thank you. Yeah. Okay, cool. So what this is telling us that there's actually two different types of redirection. And so the first one, the way that we interpret this is if you're calling from, if the call was made from kernel32.dll, then it redirects to kernel-based.dll. But if the call was made from star.dll, that's not kernel32, then it goes to kernel32. So there's actually like two levels of redirection, which is a pain in the butt. And so what we could do is we could then open up kernel32.dll. There will be a function called setThreadToken. That function will then just call the import, which is the same API set, which would then mean that we're calling from kernel32, which then would redirect us to kernel-based.dll. So that would just waste a little bit of time, but it would look exactly the same. And so we're going to jump straight to kernel-based.dll. Okay. Where are you? Okay. I don't need that anymore. So what we're going to do is we're going to drag and drop again. So this is a process that takes a little bit of time, especially when you're first working on it. But you'll find that it becomes very, very fast, and things tend to do it the same way every single time. And so as you do it more and more, you'll kind of know what to expect before you even do it. All right, so kernel base is still processing. Again, we don't have the graph view, so there it is. Okay, so then we could go and look for set thread token. Okay, and so there's a little bit more going on here. Okay, not a whole lot, but the way to interpret this is it starts here, and then there's a jump, which is a branching instruction. So you could go one way or the other. And depending on kind of the result in the situation, it's going to go either. Okay, I was like, oh crap, that's not good. It's going to go one way or the other, right? And so, but eventually, both branches will call this function nt set information thread, right? And so now we could go to the import table, and we could look for nt set information thread. And one thing to notice is there's nt set information, lots of things: files, processes, tokens, threads, virtual memory, object keys, so on and so forth. But we see that it's implemented in ntdll. So we do the same thing. Okay. Let's just load the, of course, reload file. Okay. It's like, hey, we've already done this before. Do you want us to do it? And I'm like, yeah, that'd be nice. And then it's like, I can't actually, psych. I was trying to save us from having to sit here while this parses. Okay, so we can do the same thing just without waiting. Nt set information thread. Okay. And we click on that and see it's not in the nice block, but what we see, looks like it's getting ready. Come on, there we go. What we see is that there's this syscall instruction, right? So that means that we're at the point where we're calling the syscall, transitioning the processor from user mode to kernel mode. And then we're going to call the D, and so I think we just push H, and that gives us the decimal version. So the hex version, which is the 13th function in that table. Now, these numbers are going to change from operating system to operating system. So every version of the operating system, that table changes slightly. And so that's actually one of the hard things about making those tools that do direct syscalls is that you have to be able to handle a bunch of different operating system environments. Okay, but so that kind of builds out our structure. All right. Does anybody have any questions about that flow? Okay, so that would be the lab walks through that in like excruciating detail. So it's like literally step by step. And so I highly recommend that if this intrigues you by the end, do the lab. And then there's going to be we're going to talk about probably 15 different functions. And in theory, you could do the same thing for each of those. And the lab serves as kind of a guide. So it'll be specific for this one, but you just kind of replace the words and it will work. So it'll take a few to kind of get used to it, and then you should be pretty good. So what we do is we then build out the function call stack. So we have remember the function chain is this horizontal thing. And then vertically, we have the function call stack, right? And that's going from the high level function that was called, which is this red circle, set thread token from ADV API 32, all the way down to the syscall. Okay. And so the idea again is that the attacker, when they write their malware, could call any of these and they would be interchangeable. And so you can't just assume that they're going to call the function. Okay. Now, what we have is, this is like I pull it out of the oven, right? So if you were to go through all the different functions that we had interacted with, right, in samples 1 and 2, you would have open process token, duplicate token, set thread token, close handle, close handle, close handle. Now, the reason why this is interesting is because attackers can choose any of these functions. And so while they chose this top row here, right, that's only one variation that's represented by this graphic, right? They could choose the direct syscall approach, which is this bottom line here, but they could choose any arbitrary combination, right? So you could do this in a bunch of different ways. Turns out there's 158,750 different combinations of functions that are possible. And so if we tried to represent every function chain that's possible, we'd be screwed, basically, right? So there's an infinite number of particulars, right? So of tools that are literally unique, there's an infinite number of them, but there's just for this one stack, there's 158,000 variations. I'm not building 158,000 different detections. That's just it's not practical, right? That's still too many. And so there's like more abstraction that we could add into this, and it'll be fun. Now, the next question is what's going on with impersonate logged on user? Remember, that was the one that was like, they skipped duplicating the token and it's a different function. Well, let's kind of do the same thing, okay? I'll try to do this one a little faster. So impersonate logged on user. Let's just go and look at the documentation. So again, impersonate logged on user function lets the calling thread impersonate the security context of a logged on user. The user is represented by the token handle. Okay. If you scroll down to the bottom, we see that it's also implemented in ADV API 32.dll. Cool thing is we've already loaded that up. And so we could just go back to it. Okay. All right. So here we go. We're going to the exports table, right? Impersonate logged on user. Double click on it. Same thing, right? So just this was the same for create file. It was the same thing for set thread token. It's the same thing for impersonate logged on user. It just is a jump. So they call this a stub, right? And the stub is just a jump into an imported function. We go back to the import table, impersonate logged on user, and we see that it's implemented by the API MS Win Security Base L1-2-0. So I did close this, but let's just, okay. So then we just do get int API set. Okay. There we go. And we do the same thing, API MS Win Security Base -L1-2-0, and then we'll do select expand property hosts. Okay. And so we see, again, it's implemented in kernel base. So this time it doesn't have the 2 layers of redirection, it's just the 1. But we could go back to kernel base and we could look at the same thing. Impersonate logged on user. Now, impersonate logged on user is a little bit different. So you get one little trick that you can do in IDA is come look at the graph overview. And like I'm just going to go to set thread token real quick, just so you see. Here's the graph overview for set thread token. And here's the one for impersonate logged on user. You can just see that it's a little bit more, there's a little bit more going on, right? And that's kind of a good idea for the relative complexity of things. But what we see is that there's multiple API function calls. So what we see here is we see a call to int query information token, right? We see a call to int duplicate token, right? Remember, we skipped the duplicate step, but now we see that the duplicate step is actually self-contained. It's contained inside impersonate logged on user. We see int set information thread. Do we remember seeing that previously, right? So set thread token called int set information thread. Impersonate logged on user also calls int set information thread, right? And then we see int close, which is equivalent to close handle, right? So remember we saw close handle previously. So this is what I call a compound function, right? So this is a set thread token is a simple function. It just has a vertical line from the high level Win32 API function all the way down to the syscall. Impersonate logged on user actually has branches because there's multiple functions being called within a single function. And this happens to be a really simple version of a compound function. So again, we have 4 function calls: int query information token, int duplicate token, int set information thread, and int close. And if we were to go look at all of those, each one of those makes a syscall in int DLL, right? So just to kind of show, like, I don't know which one. So we already looked at int set information thread. So it's int query information token. Same thing, right? So we see a syscall, and this one it's 33, right, is the syscall number. And then we could do int close. And we see same thing. This one is 15, right? So it's you should see that there's like kind of a pattern going on. So it's you can start to make predictions about what you should expect to see, and hopefully that will when you look at it, it'll be right? That's kind of the general idea. But if we go back to our slides, we now have, this is a function call stack for impersonate logged on user, right? And so you see that it gets all the way down to kernel-base.dll, but then it branches off and it calls a bunch of different functions. Okay. And so we have numerous syscalls that are being made. Int query information token, int duplicate token, int set information thread, and int close, right? So that gets into this idea of okay, well, so the idea that a single function can call multiple functions internally, and the idea that we had that 158,750 different variations, that tells us that maybe there's a way that we could represent that more abstractly. Just like we have the Australian Shepherds, what if we could just call it a dog and detect dogs instead of detecting Australian Shepherds, right? And so, it's called a dog catcher, not an Australian Shepherd catcher, I guess. And so that's this idea that I call an operation, right? And so operations are abstract categories that basically contain interchangeable individual function calls. So the idea that I could call int close or close handle and they're interchangeable, I should just ignore the difference between those two things and give them a label that labels the entire group of functions that are interchangeable, right? And so there's this idea to where the entire stack could be represented by a single node in this graph or whatever. Now, there are certain situations to where you might have two independent stacks. Like, for instance, there's a function that we saw called duplicate token, and then there's another one called duplicate token ex. And neither one of those functions, like they don't end up calling the same thing, right? So they're independent stacks, but they essentially do the same thing. One just allows you to change some details about the token, and the other doesn't, right? And so even those two individual function call stacks, they would probably be represented by the same operation, is kind of how we go about it. Now, the way that we define an operation is an action taken against a securable object. So that maybe introduces the need to explain what a securable object is. You all probably know securable objects, even if you don't know them by that name. But a securable object is essentially, in Windows, anything that you can get access denied from, right? So who here can think of something that you've had access denied trying to do? There's like a really, really common one, and then there's some more esoteric ones. A file, right? So the file is like the archetypal securable object, right? So you say, I want, person A to have access, to read access, for instance, and I want person B to have no access, right? And so they would get access denied. But you have registry keys, processes, name pipes, threads, tokens, services. There's all kinds of different things that are securable objects, right? And all of those things, there's a certain number of actions that you can take against them. So for instance, you can create a process, you could terminate a process, you can read the memory of a process, you could write to the memory of a process, you could do all kinds of different things with the process. So the action is for instance, in the statement process create, process is the securable object, create is the action. Registry key read, registry key is the securable object, read is the action, okay? And this is actually how we talk. So I don't know if people were in for the panel discussion that we did before lunch. One of the things that I talked about was this idea how this idea of snake detection theory, and this idea that the theory posits the idea that evolution has helped to shape primates' vision, right? Such that we see the things that we need to see in order to survive, right? So the idea is that our ancestors who didn't see the things that they needed to see to survive, they died, and then they didn't reproduce over the kind of long span of history. And so the idea is that we tend to see things that we need to see because otherwise we would have been eaten, or we would have fallen off a cliff, or we would, there's all kinds of different reasons. And so then there's this idea that the way that we talk about things is potentially evolutionarily adapted. And so when you talk about your event logs, for instance, you say, I have a process create event, right? I have a registry key read event. I have a file delete event. That's how we talk about the event logs already, right? And so it's kind of a natural thing that nobody really thinks about, but it could be expanded much further than the way that we currently do it, okay? And so the idea is that operations allow us to ignore the differences between, say, kernel. This is actually an interesting thing. So there's a certain notation. We talked about how you have set thread token in kernel and ADV API 32, but you also have set thread token in kernel base .dll. And then it's like, okay, they have the same name. There's actually a way to represent what DLL you're talking about. And that's you write the name of the DLL, and then you do an exclamation point, and then the name of the function. So that's the kind of convention for writing how that what you're talking about and being more specific. But if I want to ignore the very minute or less significant differences between kernel 32 open process and NTDLL NT open process, I could just say that's a process open or process access event, right? If I want to ignore the difference between, say, ADV API 32 set thread token and ADV API 32 impersonate logged on user, the question is can I do that, or what are the implications of it? And so in order to do the naming convention, at first we just kind of like did the naming however we felt, and then we kind of reverse engineered like how do we come up with the names that we came up with, and does it actually make sense, or are we just like sticking a finger in the wind and hoping that it works? And we use a grammar heuristic. So at least the way English works is you have subject, verb, object. I think French is probably the same, right? Are most people French speakers? I kind of like him. Look, no, everybody. Okay. Okay. Well, then the way that we speak is through subject, verb, object, right? And so like if you were to talk about the thing that you're interested in seeing in your event or whatever, what an event is telling you in a full sentence, you would say the process named beacon.exe enumerated the subkeys of the registry key named HKLM system current control set services. That's like the full sentence, right? But if you were to break it up, you have the process, right, is the subject. What did it do? Well, it enumerated something. And what did it enumerate? The subkeys of a registry key, right? With a specific name, right? And so what you could do is you could say a process enumerated a registry key, right? So this was something that Roberto Rodriguez, the guy who did the keynote, he kind of like first introduced this, him and his brother. And so what we do is we say, we take an objective point of view. So when people say like, oh, that's subjective versus that's objective, like, oh, like I'm making an argument, it's like, hey, this is objective. I'm not like, you can't argue this. What people tend to do is they use subjective to say, that's just your opinion, bro. And they use objective to say, you can't argue with me because like, this is scientific or whatever. But what that really means is what point of view you're looking at the problem from. And so are you looking at it as the subject of the experiment, or are you looking at it as the object that the action's being taken upon? And so what we're doing is we're taking an objective point of view, right? Because we're saying it's a registry key enumerate event. Like that's the name of the operation. Well, the registry key is the object of the sentence. It's not the subject. You wouldn't say it's a process enumerate, because what did the process enumerate? Right? The process can enumerate tons of different things. And like the process has to, like the thing doing the enumeration is always going to be a process. So that doesn't give me that much information, right? Just like this, the process named PowerShell.exe created the file named cwindowstemp.a.txt, right? We call that a file create because process is the subject, created is the verb, and then file is the object. And so we take the object file, and we take the verb create, and that's how we come up with the name. That's the name. That's like the heuristic for how we do that. Now, the other problem with the subjective point of view is that there's actually numerous subjects, right? So there's the subject, which is the process. There's the subject, which is the user, right? So a process, PowerShell.exe, is running as a user, Jared, right? Which is then running on a computer like workstation A, right? And so simultaneously, you could say that the process created a file. You could say that the user created the file. You could say that a computer created a file. And so the object, the file that's being created, there's only one way to interpret that. And so that's why we take the objective view. All right. So there's potentially some more complicated ways to start getting into, not every single function call stack is going to lend itself to being understood as an operation just through that grammar heuristic. And so what we are going to do is kind of talk about a methodology for how you would go about determining what the object of the function is, right? So on Windows, there's kind of two special classes of functions. There's open functions, and so there's like open process, open service, open process token. I can't think of any more off the top of my head, but we could actually literally just go look. So those are typically implemented in kernel 32, which happens to be the one that we don't, we could look in kernel base. So if we go to kernel base and we type in open, we see open event, open file by ID, open file mapping, open thread token, open state, open semaphore, open process token, open process. There's tons of different open functions, right? And so those are kind of like meta functions because they're just opening a handle to a process or to an object. They're not actually performing an action. So the way that a lot of objects exist in kernel mode, right? So like processes exist in the kernel, they don't exist in user mode. And so you can't just like query processes from a user mode application, from like a random application or malware that you're running. What you have to do is you have to open a handle, which goes through a authentication process or an access control process and say, hey, I want to kill this process. And then what happens is the computer says, okay, well, you're running as Jared, and Jared does not have the ability to kill this process, to terminate the process. And so what we're going to do is we're going to give you an access denied error. That's what happens. And so if I want to do something with a secureable object, I have to first open a handle, which allows me to go through that access control. And then I can subsequently do the operation, the action that I want to do. So, but you also have these create functions, right? So create directory, I don't even know what some of this stuff is, create enclave, create fiber. So you have processes, then you have threads, then you have fibers or like smaller threads. Who knows what's going on there. Create file, create mutex, create name pipe, so on and so forth. So create process. So there's some trickiness with this. For instance, create file, there is no open file because create file both creates files and it open files. So that's just like some stuff that you learn over time. But generally speaking, you can assign open as the action to anything that has open in the function name, and you could assign create as the action to anything that has create in the function name. Okay. And these are going to be where your access control happens, right? So secureable objects, they all have DACLs, discretionary access control lists, and those are going to specify who could do what with the object. And the access control lists are going to be checked upon the calls to opens or creates, basically. Okay. And then once you have the handle, you can then use that handle and pass it to subsequent things like terminate process. If you want to terminate a process, there's a function called terminate process. If you want to read the memory of a process, there's read process memory, right? For a token, there's get token information if you want to know stuff about the token. There's also duplicate token, which we saw called here. Okay, so there's kind of this. Now for all other functions, set thread token is an example. Like what does anybody have an idea for what the operation for set thread token might be? This is like okay. How about duplicate token? What do you think the operation name for duplicate token would be? That one's a little bit token boom. Yep. Yeah. So it's like a trick question because it's so straightforward, right? You just like take the first word and replace it with the transpose them, I guess. Okay. So the steps for doing this in kind of like a little bit more of a fixed way or a repeatable process is if the term begins with open, then the action is going to, then the target object will be the object that's being opened, right? So if it's open process, then it'll be a process will be the object, right? If the function only takes one parameter of type handle, right? So you want to look for handles, but if it takes one parameter of type handle, then the handle usually will represent the target object, right? So one example of that would be, let's see, terminate process. So we'll just look at terminate process. Okay. So if we come in here, remember this is the thing that tells you how to interact. It's the syntax, right? So the way to read this is the name of the function, terminate process. This is the output type. And the output type is a Boolean. So Boolean means true or false, basically. So it's either going to say true, the process was terminated, or false, the process was not terminated. These are the parameters, right? So there's two parameters. the first parameter is named hProcess, and it's of the type handle, right? And it's something that has to be passed into the function. The second one is called uExit code, and it's a uint, which is just basically a integer, right? And so there's like this naming convention to where h just tells you that that's a handle, right? And then u tells you that it's a uint, right? But this is an example of a function that only takes one handle, and the handle happens to be a handle to a process, and it says that more explicitly here, a handle to the process to be terminated. And so now we know that the object of this function, or this function called the associated function call stack, would be a process, right? Okay. Then there's situations to where they take two or more handles. So it's easy when there's only one handle, because you just say, what is that handle? Okay, that's probably the object. But what about when there's two handles? How do you choose which one? So duplicate token is an example of this, right? Okay, so duplicate token also outputs a Boolean, but we see that there's a handle here called and this one is a little bit easy because you'd probably get it right if you just guessed, because they're both tokens. But this one is a handle to a token, the existing token handle, and this one is a pointer to a handle to a token, which is called duplicate token, duplicate token handle, right? And the way that you would figure this out on this one is by looking at this first column here, right? In versus out. In means that you need to pass the value into the function. Out means that the value is going to be passed out of the function as an output, right? And so in this case, the input is going to be the object, which is a token, right? Because this is actually the result. This is the duplicate that you get, okay? And then you also have situations to where so the idea here is that if you have two or more and only one is an input parameter, then the one that's the input parameter is your object type. And then you have of course, they make it hard to where there are some that have two or more, and all of them or more than one of them are going to be inputs, and set thread token happens to be that example, to where there are two handles being passed in. One's a thread and one's a token, so you can't just guess. And they're both inputs, and they're actually both optional, which is kind of a pain in the butt. And so how do you figure that out, right? One trick would be to basically say, hey, this one's first. So that might be everyone that I've looked at, the first one happens to be the object. I don't know how far that will get you. But you could also look at the syscall that's being made, right? Int set information thread, right? And so generally speaking, for this type, there's like int set information, int query information, int write information. So there's always going to be, and then there's some object, right? So in this case, it's a thread object that's being set, just kind of means write, right? So there's set, get, query, and a couple other ones, but set kind of means write. And so in this case, you're writing to the thread, you're not writing to the token, right? And so in this case, we would see that the handle of this is the syscall, basically, right? The kernel function is a thread. And so we would figure it out that way. Okay, so there's kind of like a hierarchical way to figure this stuff out. Okay. And so here, read process memory is just an example of the first type where it only takes one handle, right? hProcess. So we know that that's interacting with a process object. This is duplicate token, the one that we just talked about. And then we have set thread token, which was the third example. And we went down and looked at the native API, or the syscall int set information thread, and it only took one handle, which happened to be a thread handle. Okay. So then we have the action, right? So we kind of have at least a little bit of a method of figuring out what the object is, but how do we figure out the action? So one way would be to visit. So this is the steps, I guess. Visit the documentation for the function in question, set thread token, duplicate token, whatever it is. Find the description for the object's handle type parameter. That we just did that, right? Which handle do you look at? Identify any reference to a required access rights or access to required access or access rights, right? So say something like a handle to a blank, opened with blank access. It's kind of what you'll look. Then you can Google object, so token or process or registry key, security and access rights, and visit the page, find the referenced access type, and then match it as closely as possible. So just like you did, if it's token duplicate, you would just say duplicate would be the action, okay? And so we'll kind of do that real quick with duplicate token. Okay, so here we are on duplicate token. Remember, we were looking at the existing token handle here. And here we see the existing token handle is a handle to an access token, right? That's our object, opened with the token duplicate access, right? And so now we could go and do token security and access rights. Okay. And this is what we would get as the first result. And we could come in here, and here's all the different types of things that you can do with tokens, right? So you can adjust the default settings, adjust the groups of the token, right? So you could add the token, add additional groups. You could adjust the privileges. So if you've ever heard of like SE debug privilege, SE backup privilege, all those types of things, that's all housed inside of the token. You could adjust the session ID, but you could also duplicate it, right? And so then we would take that as our action. And this actually serves as a guide for the different types of actions that you could perform on a given object, right? So if you have a token object, this is kind of the set of actions that you would expect to see on tokens. We could do the same thing for like read process memory. All right, so you have read process memory. The first one is H process, a handle to a process with the memory that's being read. The handle must have process VM read access rights. So then we could do process security and access rights. It's the first. Microsoft paid for the ad, so now it's the top result. And we come in here and we can see the types of things. So you could create processes, you could create threads, you can duplicate handles, you could query information, you can read the virtual memory. So these are the types of things that you could do with types of actions you can take against process objects. Does anybody have any questions on that? No? Cool. So let's look at how that turns out. So now what I've done is I've taken our function call stacks. This is open process token, duplicate token, set thread token, and close handle. And I just added an operation bubble at the bottom of the function call stack, right? And then what you do is now you could connect them, right? And so what you end up with is something I call the tool graph, right? And so this is the tool graph that represents samples 1 and 2, right? So remember, we have the function chain, we have the function call stack, and then we have the operation chain. And so what we're doing is, instead of thinking about those 175,000 or whatever different, or 183,000 different variations, we're going to summarize them, right? So we're going to summarize 183,000 variations in one operation chain. And we're going to say, hey, there's 183,000 variations, but they're actually so similar that we could ignore them, right? Assuming that we think about things at an operational level, right? Okay. So that's like in taxonomy, you know how you have the species, genus, order, family, like the kingdom, phylum, whatever. Each one of those is called a rank in a taxonomy. And so we're going potentially from the species rank up to the genus rank when we go from function chains to operational chains. We're just going one level of abstraction higher. And so, yeah, here's the math, how that all works out. So in this tool graph, notice that there's 1, 2, 3, 4, 5 functions, right? For open process. So we have to choose one function from each of these columns if we are building a tool. And there's 7 functions here, 6 functions here, 7 functions, 5 functions, 5 functions, 5 functions. And the way that you figure out the number of variations is simple multiplication. You say 5 times 7 times 6 times 7 times 5 times 5 times 5, and you end up with 183,750, right? But this one operation chain describes all 183,750 different variations, right? So it's just a way for us to summarize or abstract away the complexity. That's what abstraction is, right? The reason why we talk about dogs instead of like, if I want to tell you about my dog, I say, I have a dog, and you get this warm, fuzzy feeling inside or whatever, if you like dogs. I don't have to tell you every little detail about my dog in order for you to kind of understand what it's like to have a dog, right? I don't want to tell you, oh, well, they called this. I don't want to have to explain every single bit in a program to be able to explain what it does. I say, hey, first it opens a process, and it opens a token, then it duplicates the token, then it, applies the token to the thread, right? And so I could explain it at a higher level of abstraction and still get the vast majority of the point across. And the idea is that if you can start to use that level of abstraction in your detections, you start to have more coverage as a result of it. Does anybody have any questions about that? No? Okay. So we can do the same thing with impersonate logged on user. And so what we end up with is a single function. So previously, every function that we called in the function chain corresponded one-to-one with an operation. But impersonate logged on user is a compound function, and the definition is essentially a single function that corresponds with multiple operations, right? That performs multiple operations. You can almost think of this as like a miniature application that you're embedding inside of your application as a developer, right? And so what we see is, this is actually a typo here, but we have token query, token duplicate, thread set, and handle close, right? And then we end up with a graph that looks like this. And I'm going to skip that because it had the picture of what I'm doing. And so you probably saw it already. But now what we can do is we can do a comparison at both the functional level, right? Which is, hey, at the functional level, these two things look pretty different, right? There's some things missing. There's a different function call. It's different. But at the operational level, they look pretty similar, right? And so if we were to do an analysis at the operational level, we notice that they're exactly the same, except this one does a token query operation. And the interesting thing, which we're going to talk about in a second, is the token query operation is not mandatory. And you might think, does anybody know how we know that it's not mandatory? Because this one doesn't do it, right? So this one does all the same operations, except it excludes token query. And that tells me that token query is not a mandatory step. It's just a nice to have, right? And so basically, like what we're seeing is that, hey, these aren't exactly the same, and they're different at the functional level, but they're similar enough that they're probably the same species, right? And so here we have a different breed of dog. That's basically what we see. And so we have a Doberman instead of Australian Shepherd. But like there's a lot of things that they have in common. Okay. Now, the reason why, like I'm saying you should think about things at the operational level. The reason why I say that is because we actually see things at the operational level, right? So I kind of alluded to this previously. So this is an example of an operational chain for process injection, right? So there's a bunch of different ways you can do process injection, but this is like classic shellcode injection or whatever. And the way that it works, you've probably heard the functions before, right? So you have open process, virtual-alloc EX, write process memory, create remote thread. When I was like first starting out in the industry, and I wasn't a programmer at the time, I had no idea what any of those things were. Somebody was like, hey, if you ever see virtual-alloc EX, write process memory, create remote thread, you're seeing process injection. And I was like, all right. And I just like locked that away. And then every time I would analyze like a suspected malware, I would look for those words. And I had no concept of composability or what they meant or how you could interchange them with things like int read virtual memory instead of read process or int write virtual memory instead of write process memory. I had no idea about that complexity, but I was just looking for those. But it would have been better had that person explained it to me by saying, hey, if you see process open, memory allocate, process write, thread create, you're seeing process injection. Now, if you think about MDE or your EDR, right? What do you actually see? What are the events telling you? And what's interesting, this is a perfect example because what you find is that Microsoft Defender for Endpoint in particular happens to have a single event for each of these operations, right? So they have open process API call, which tells us about process open. It has memory int allocate virtual memory remote API call, which corresponds with memory allocate. It has write process memory API call, which corresponds with process write. And it has create remote thread API call, which corresponds with thread create. Now, they've actually named the events after the high level function, but the logging occurs in the kernel. So it actually gets the whole call stack, basically. So there are some caveats with MDE to where it does some filtering. Like, for instance, Olaf's the expert on this, but open process, I think, only applies to LSASS. Yeah, so some of them aren't going to be like comprehensive. However, there is an event that corresponds with each operation in this operation chain. And so then the question is like, okay, well, which one would I prioritize, right? So if I could see each operation, which operation do I pick? Because you have to pick one, right? You could do correlation and you could say, oh, if I see X and I want to look for Y, but you have to pick one. Does anybody have just like a gut feeling on which one of these operations you would rather look for? Create remote thread. Okay. Anybody else? Anybody have a different opinion than that? So that's the answer. There actually is like a proper answer. And the reason for that is that as you progress, so there's this neuroscientist in the UK named Carl Friston, and he has this theory called what the heck is it called? It's going to come to me later. Anyway, the general idea is about every decision that you make in life is about path, like selecting which path you should go down, right? And so imagine that you have a goal, and your goal is to have $1 million in your bank account, right? Well, there's an infinite number of paths that you can take to pursue that goal, right? Yeah, one way is you could go to the bank and rob it, right? Another one is you could buy lotto tickets every day until you win, right? And the other one is you could save $100 a week or whatever for 70 years, right? But all of those are paths that could potentially progress you towards $1 million. Some have higher chances of succeeding. Others have, they'll happen faster. So so the principle is called the free energy principle. And the idea is that what organisms are trying to do in life is reduce free energy, which are free energy is the element of surprise. So when generally speaking, when you become surprised about something, that means that you didn't predict it, right? And so surprise isn't necessarily bad, right? Because you have good surprises like surprise birthdays, right? A surprise birthday just means that you thought that your significant other didn't love you, but then they proved to you that they did because they had this surprise, right? So, but generally speaking, surprise is bad. And the reason for that is, has anybody read, there's a book by Simon Sinek called The Infinite Game. So there's this idea called of the infinite game, right? So like if you think about sports, you think about what we call finite games, right? So like a basketball game, there's rules that are very constraining on what you can do. And there's a finite amount of time. And at the end of 4 quarters, which are, 12 minutes long or whatever, then the game's over, right? And whoever has the most points wins. But you could also think about basketball, for instance, in the context of an infinite game, right? So it's like, well, are you playing a game that consists of one game? Or are you playing a game that consists of 82 games, which is a season, right? And like, do you want to be the winner of this individual game, or do you want to be the winner of the entire season? And then like, are you playing a game that consists of one season, or are you playing a game that consists of multiple seasons, right? And so then you start talking about like dynasties in sports and things like that. And so like life, for instance, is an infinite game. And the problem with surprises is that the high end of good surprises is like infinite, right? You could be infinitely surprised in a good way, but the low end of bad surprises is you're dead, right? You don't get to play the game anymore. The game ceases to exist. And so generally speaking, it's in our best interest to minimize surprise as much as possible, because surprise can either be good or bad, but bad surprise is way worse than good surprise is good, if that makes sense. And so what we try to do is we minimize surprise. So anyway, I said all of that to say this. The idea is that there's a number of paths that you can take, right? And so let's say that we're trying to see process injection, right? Well, process injection, if you use this method, we know that we've injected when the thread is created, right? And so that's kind of like the impetus that says process injection has occurred, right? And we're dealing with uncertainty otherwise, right? And so as we start to back up, there's multiple paths that can be taken that aren't going to result in process injection. So for instance, I can open a handle to a process to terminate it. I can open a handle to a process to create a thread. I can open a handle to a process to read its memory. I can open a handle to a process to do a bunch of things, right? And so all of those other things that don't progress towards creating a thread, those are all false positives, right? Those are all paths that are not the thing that I'm actually interested in. And so the idea is that the further along, it's actually not the further along in the chain. Sometimes you could do there could be operations after kind of like the inflection point. But if you look at the open process, it's going to be more susceptible or more susceptible to false positives than the thread create, right? Because there's a finite number of reasons why you would create a thread. Some of them happen to be process injection. Other ones happen to be multi-threading applications, things like that. But there's a whole lot more reasons why you might open a handle to a process than there are create a thread. And so mathematically, it's better to do thread create. Now, there are situations to where your EDR might not have the thread create event. And so you have to take a less valuable or a more error prone operation as your base operation. But generally speaking, what you want to do is you want to say, which operation gives me the most information towards discerning that this thing happened that I'm interested in looking at. And that's what I want to start with. And then you go from there, because that eliminates the most bad paths, most surprising paths. Okay. All right. And then there's this, this is like a rant slide, I think, but there's this thing that I call the implicit process create. So has anybody like been to a presentation where people talk about data sources and they show this graph of like, we looked at MITRE ATT&CK, and MITRE ATT&CK references data sources, and process command line parameters is the number one data source. Does anybody create like, has anybody thought about like, if I could have one event, what event would I want? And then the answer is almost always process creation, right? And the reason why people think that is they're like, oh, well, process creation applies to everything, right? I could like, everything that bad happens from our process. And so if I have process creation, I could apply that to everything, right? Here's the problem with that. So if we look at this operation chain this is again, process injection. Do you see a process create event or operation? No, right? That's weird. But like you could detect process injection with process create events, but there's no process creation operation. That's because process creation in most cases is subjective, right? There's a subjective perspective of the process. The process is doing the action. Everything that happens on a computer happens through a process. And so there's always a process, but the process is the subject, not the object, right? There are other situations, which we have an example that we'll look at in a second, where process creation is part of the operation chain, right? And by being part of the operation chain, that means it's objective, which means there's going to be some static aspects to it. So the problem with subjective process creation is that everything is dynamic. You could change the attacker has full control on everything. They could change the name of the process. They could manipulate the command line to bypass your regex. They could do all kinds of different things to hide or make themselves blend in or appear different, right? But in the objective sense, there's going to be certain things that they can't manipulate, right? And so that's why when you're doing your detection, if you're doing, there are cases where you want to do that subjective process detection where you're looking for, like if somebody runs mimikatz.exe, you want to detect that regardless of what it does, right? There's nothing good. That's that surprise thing. It may not be bad, but it probably is. And if it is, you're going to look stupid. So that's kind of the thing you got to be careful of. But if you're doing a behavioral detection, you should be thinking about it objectively instead of subjectively. All right. So there's this idea that we have called simplification, and we kind of already touched on it a little bit, but there's in every operation chain, there's going to be a subset of operations that are non-necessary, They're things that people could just leave out if they wanted to, right? So it's like, I don't have to do that. And one of the examples that we talked about was token query, right? We said, oh, how do we know that token query is not necessary? Well, the answer is that this one doesn't do it and this one does. So the fact that this one actually works means that it's not necessary. Okay. So what we could do with simplification is we can reduce combinatorial complexity. So, we had 183,000 different variations. Well, if we remove the functions or the operations that are unnecessary, we can remove the number of different variations that we have to worry about, right? And we can talk about things at a more specific or a more abstract level, okay? And so what we could do is we can start to look at which operations can we exclude, right? Which ones are not necessary to actually achieve the outcome? And this goes back to that composability thing, right? One way that you might go about looking into this is like token open. Okay, what was the function that corresponded with token open? It was open process token. So let me go look at that real quick. Open process token. So open process requires a open process token requires a handle to a process, right? And then the question is like, well, how do I get a handle to a process? Well, the way that you get a handle to a process is through open process. Okay. And so that means that it is necessary for me to call open process in order to call open process token. And then it's like, okay, well, I need to call duplicate token next, right? Well, in order to call duplicate token, I have to have a handle to a token, which means that it's necessary for me to call open process token in order to call duplicate token, but it's necessary for me to call open process in order to call open process token. So there's this composable requirement to where all three of those things are mandatory. And then there's ultimately set thread token, which is the one that I actually wanted to call. That would be the one that we want to detect eventually, right? And so that's something that requires a handle to a token that you want to apply to your thread, which means that you have to call duplicate token, which so on and so forth. Okay. All right. Then the other one, does anybody have an idea for what another operation that we can exclude would be? I think I alluded to it earlier. The which one? Handle. Yep, close handles. Yep. So in theory, you could just leave the handles open if you wanted to. I mean, legitimate programmers do that all the time on accident. And yeah, actually, like bad guys are probably it's actually if you see handles being closed, all the handles being closed, you know that you have malicious application. But generally speaking, there's not like in the short term, nothing's going to break if you leave your handles open. And so if we built a detection that was looking for handles being closed, the evasion would be just leave them open and then we would never detect it. So it'd be that's just a bad idea, right? And so we can exclude that. And so what we end up with is this reduced or simplified operation chain, which now is a little bit more straightforward. There's only 4 operations that we have to deal with. Does that make sense? Yep. And so what happens is when we simplify sample 1, 2, and 3, the operation chains are identical, right? And so now this is what the dog operation chain looks like, essentially, right? And so we have this idea morphologically, right? Morphology is the structure. The structure of a application would be the bits that it has integrated into it, which then represent the functions, which represent the operations. This is like if you were to think about us, it's like, okay, well, when we think about morphology, we think about, oh, you have 2 legs, you have 2 arms, you have a heart, you have a brain, so on and so forth. Well, your brains are made of cells, right? And so those cells go into, I don't know, components of body parts, and then components compose together to form full body parts or whatever. So it's kind of an analogous kind of idea. Now, we can look at, so at the operational level, that's what a dog looks like, right? So it's process open, token duplicate, thread set, right? That's dog. And I just for anybody wondering, I just made that up. There's no actual reason why I chose a dog. It could be any animal, but it just made the next part a little bit easy to kind of explain. So here's a 4th sample, sample 4, and sample 4 calls log on user, impersonate logged on user, and close handle, right? So one thing that I'm hoping you're kind of like seeing, so doing all that stuff I did in IDA is kind of a pain in the butt and it takes a lot of time. One of the feedback things when I tell people that is like, well, it just takes a long time. And it's like, well, yeah, but it may take a long time, but what you find is you see the same functions over and over and over. So if you keep it once, you're good to go. So just to kind of show how simple that is, right? We see impersonate logged on user. So if I'm trying to build that graph, maybe this is something I should have mentioned earlier. There's this application called arrows.app. So if you just go on your browser and type in arrows.app, you'll come to this application. It doesn't look very fancy right now. But what you could do is you could like add these circles and you could change the color of them. And you could end up constructing the things that I'm showing you, those graphics that I'm showing you. But one of the things that we did just to help ourselves, I mean, to be honest, is we created this. It's in the same GitHub user as the workshop's GitHub. We started constructing these function call stacks, and then we would export them and save them, right? And so, for instance, I could go to impersonate logged on user.json, and it's just this long JSON file, and you could just copy it, and you come here and paste it, and for whatever reason, this thing is like, it's crooked and annoys me, but okay, there we go. Okay, and now you have that there, and it's like I looked at it once, and now I have it stored. And if I ever run across that again, I don't have to go through and do all the work. And then the other one that we saw, I think, was close handle, right? So that's in kernel 32. Close handle, Control C, boom, there it is, right there. So what we end up with is now we have. And it has some like nice little features. Like if I want this to be equally spaced, then I just do that and like see the vertical line that just tells me, hey, you're good. And then you could just draw your arrow. I'm like very OCD. So all the arrows have, there's certain color, there's certain meanings to certain colors and things like that. And everything has to be lined up. So I spend lots and lots of time doing that. But so we have that, right? And so we're kind of just like building this thing out as we go. Now we could do the same thing. We do have a function log on user, which is new, right? That's something we haven't seen before. We have I think log on users in kernel 32. Oh no, let's see. User 32. Okay. Nope. Maybe I don't even have. I thought I made sure that we had all of them. Well, crap. Okay, so is it an ADB? No. Okay, well, we don't have log on user, so we'll do that again for the next one. But log on user is just another function, right? And so we go through the same process. We're going to do it a little bit more rapidly. This is, I think I made the cooking show joke already, but this is like the cooking show to where it's like, oh, I already have sample 4 in the oven, and so we'll just pull that out. But this is what the tool graph ends up looking like, right? And so we have user logon, token query, token duplicate, thread set, handle close, right? So if we were to just look at the operation chain, does anybody see how this differs from what we've seen previously? No, well, we haven't seen a process create yet still. What'd you say? There's no open handles, right? So we're not calling open process open or token open, but instead we're calling user logon. So is anybody familiar with Cobalt Strike? Yeah. So Cobalt Strike has this feature called make token. And what this is doing is this is implementing like an analogy of make token. So the idea here would be previously when I talked about token theft, I talked about it under the context of like, I'm on a computer already, and I see that Olaf is logged in. And so then I want to steal Olaf's token, right? But what do I do if I have a username and password and that user's not logged in? So I have a username and password, the user's not logged in, but I need to become that user. Well, Cobalt Strike's answer to that is this thing that he called make token. And the way that you would do that is you would take your username and password, you would log that user on yourself. You would just say, I want to log on as Olaf, right? He's not logged onto the computer. And as you log him on, it creates a logon session, and it gives you the access token for that user. And so then you just say, okay, well, now I want to impersonate this access token that I got as part of logging Olaf on, right? And so that's what's happening here. So it's the same process. The only thing that changes is how do you get the token? So we call that like token obtention, or how you obtain the token. But so imagine that token theft is broken into how do you obtain the token and how do you apply the token, right? And so here we see a difference in how you obtain the token, but we see the token being applied in the same way, right? And so we could do the simplification process, token queries out, because we previously saw that token query was just nice to have, and then handle close is the same thing, right? And so we end up with this simplified version of the operation chain. And this is where we're no longer dealing with dogs, right? But we're dealing with a gray wolf right now, right? So like dogs and gray wolves are essentially the same animal, right? So one is called Canis familiaris, that's the dog, and then Canis lupus, which is the wolf. And so here we have a wolf instead of a dog. So it's very similar, but slightly different. Now, the reason why it's similar is because the change happened at the beginning, right? But if the change happened at the end, which is where we ideally want to be detecting things, right? That would be, I would consider changes later in the operation chain to be more significant than changes earlier in the operation chain. I don't know how that's going to hold up over time, but that's my current approach is like changing this would be more significant than changing this stuff up here. Okay. So it's like a mullet, you know, the business, you got party in the front, business in the back. And so you don't want to change the business. Wait, business, it's the inverse mullet, I guess, right? Isn't that party in the back, business in the front? I don't even know what I can't even imagine what that. Does anybody have like Mid-Journey on their, yeah, ask it for like an inverse mullet and let's see what we come up with. Yeah. Yeah. Cool. Okay. So then we have sample 5, right? And sample 5, we have some similar stuff and some differences. Does anybody see a difference in what's going on with sample 5? Create process with token, right? That's the difference, right? So this is exactly the same as samples 1 and 2, except they've replaced set thread token with create process with token W, right? And so, I mean, does anybody care to hazard to guess what the operation for create process with token W might be? Create process, boom, yep. See, sometimes, like I would say like 90% of the time, it's very easy, and then you get really cocky, and then it like you run into set thread token, and you're like, oh crap, I don't know what that is. Okay, so now we have this function graph, or function chain, sorry, and it ends up making this this tool graph, right? And so we have process open, token duplicate, process create, handle close, handle close, handle close. So again, now that I'm not going to look like a schmuck, hopefully. We can go and do this thing. Process open, token open. So we'll go do that real quick. So we're in kernel 32. We go to open process. I mean, this is actually a little bit harder, but because there's more functions being called. Open process token. Just kind of do a little bit of organizing. Then we have duplicate token. Okay, then we had what was it? Create process with token W. So that is, I don't have that one either. So I do look like a schmuck. Okay, I actually prepared for the next one. So this stuff will all be relevant. So we'll keep that there. All right. So we have the same deal with the operation chain, right? In this case, the reason why you might do this is, let's say that you have your agent running Cobalt Strike or Mythic or whatever. but you have something that you want to do, but you want to do that in a different context, right? So maybe you, I don't know, maybe you want to enumerate something as user X but you still want to maintain your agent running as user Y, right? For whatever reason. What you might do is you might kick off that enumeration task as a separate process, but you tell that process to not run in the context of user Y, you tell it to run in the context of user X. So the way that process inheritance works is if I run a process in the context of Jared, right? If my process creates a child process, that child process is going to run in the context of Jared by default. So that's just the default. But there's an option in this create process with token W. There's also create process with logon. There's a couple different functions that allow you to specify the user context of the child process, right? And so this is the way to do that. Okay, so we do the same thing with simplification. We get rid of the handle closes because nobody does that. And now we have a new operation chain, a new species. But this species changed a fundamental aspect of what was happening. So previously, all the examples were we were impersonating inside the same process, right? We were just causing our thread to impersonate. But now we're creating a new process that impersonates. And so the detection that you would apply to this would change fundamentally. And so now we're saying, hey, we're a fox, right? So a fox is still part of the same family, the canine family, basically. But it's not a wolf or a dog, right? It's more different, right? And so if we went all the way back up to the very top with the taxonomy, you would have seen that like fox, you have like the dog at the very bottom rank, then you have the dog and the wolf at the second rank, and then you had the dog, the wolf, and the fox at the next rank. So that's kind of where we're getting. Okay, and then the last sample is sample 6. Does anybody see something that's different here? This one probably should be a little bit weird. You're like, why'd you do that?
You ordered all the ones we already covered.
Kind of, yeah. I mean, it has a little component of each. Pay close attention to all the function names because one changed slightly. So this one calls create process W, not create process with token W, right? And this was actually, so Johnny, who was the co-presenter with me, he ended up catching a fever and couldn't make it, but he literally wrote this, and I don't think we've ever seen this in the wild. So this is actually kind of neat because we thought about how we would detect the other ones, which I'll talk about in a second. And then he was like, well, the way that I would detect the first 3, right, the dogs, right, or the dog and the wolf, is by doing X. And the way that I would detect this other one is by doing Y. Well, this actually like juxtaposes both of those and then causes it to where both detections fail. So it's kind of neat, right? So what he's doing here is instead of creating the process with the certain user context, he's creating a process with the inherited user context. So imagine you're running as Jared, you create a process as Jared, but then he's telling set thread token to impersonate. And so it's the process is created in the normal way that you would expect a process to be created. But now then it's being executed in the different way, right? So here we see open process token, duplicate token, create process W, set thread token, bunch of close handles. Same thing. So this is the one that I'm actually prepared for, allegedly. So we could go to create process W. Okay, this one's a little shorter, and I tried to get them all to be like matched up as well, so that if you just grabbed them, they worked. One thing that's worth kind of talking about is, see, this one's a different color. It's not black. The reason for that is that this is actually a compound function. But one of the things that we realized very early on is some compound functions are extraordinarily compound, and there's lots going on. And you get to the point to where if you can't do it all, you just don't do it. And so we kept getting stuck on certain ones because it's like, I'm not gonna do this for the whole thing. And so what we did is we started, this is kind of like an orangish shade, and we started using that to say, hey, we only went down one, we only did, at this point, we've only done partial analysis. And so over time, we want to build that out more. But we wanted to have an indicator that said, hey, this isn't all that's happening. It's just one branch of what's going on. So then we have set thread token, right? And I'm not going to do we could do the close handles because it's kind of cool how that works. Okay, so we got that. And then we do 3 close handles, right? So this is like why this became really cool. So you're just like boom, boom, boom. And then you could just grab all those, move them. Then you grab these 2, move them. Okay. And the thing I'm trying to demonstrate here is that the hard part of this whole process is going in and like doing the analysis in IDA. That's the hard part. And but most of the functions that you're going to see are things that A, you've probably seen before if you've been doing this for a little while, or B, something that somebody else has already seen. And so you can rely on them to do the work for you. So we're trying to make this something that's kind of open so that other people can contribute, or we just contribute whatever we do. And then you would be able to build these tool graphs without necessarily having to be able to fill in the middle yourself, right? And so hopefully over time that will grow. Right now, if you're doing process injection or token theft, it's going to be pretty good. The other techniques, probably not so much. So those are the ones that we've done pretty extensively. But it makes it a lot easier to just kind of build this out and kind of get an idea for what's going on. What you're going to find as you start looking at like real world samples, a lot of things do the same thing in the exact same way, and so they end up being functionally equivalent. But what you do is if you look at source code and you're like, okay, that calls the same functions, I can just ignore you now, and I just move on to the next one. And you want to look for next samples until you find one that you're like, hey, I haven't seen that. I haven't seen it done that way before. Now let me dig into it and see why, right? That's what we're trying to do is like the way that you start to get an idea is this is an iterative process, right? So you have to look at lots and lots of particulars and identify where there's a difference. And when you're like, hey, there's a difference. Why is that different? Does that give an advantage? Does that hinder my detection from being successful? Those are the types of things that you want to be paying attention to. Okay, so same operation chain. So again, like I said, what he does here is he obtains the token, right? And then he's like, okay, I'm going to create the process that I'm interested in doing, but that process is going to inherit the user context of the calling process, right? So Jared created the call create process. The new process is going to be running as Jared. But when you create a process, the output, this is kind of neat. Okay, create process. This is create process A. Does anybody know the difference between create process A and create process W? Remy? Yeah, so W stands for wide characters, so like Unicode characters. So anytime that a function takes strings, right? So this is a string, like the command line of the process that you want to execute. You have to specify the character set that will be used. And if you specify A, you're specifying ASCII characters, which is ASCII is technically like a 7-bit encoding, but it's 1 byte is used for each character. And that's great if you speak English or like most Latin languages. But if you speak Arabic or Korean, for instance, that's not going to work very well. And so you use Unicode characters, which is the Y. That's what W means. And what you find if you start to build out those function call stacks for create process A essentially just calls create process W. So it like converts ASCII characters to Unicode characters and then calls create process W. So they're basically the same thing. Okay. And so like, it's kind of cool. Hey, you could call create process as user, or you could call create process with logon W. Those create processes, but maybe they do it in slightly different ways, right? But one of the things that you'll see is that one of the outputs is this process information. And so if we go all the way down here, we have the process information structure. And one of the things that it does is it gives you a handle to a thread, right? And that handle to a thread is the primary thread of the newly created process. So processes can have multiple threads, but they always have at least one thread, and that one thread is the primary thread. That's the thing that's doing all the major work, basically. And so when you create a process, you automatically receive a handle to a thread. And then if we go back and look at set thread token, this is... I thought I would have a quick link. Set thread token. Remember, previously we had been passing null to the thread parameter because we wanted to apply it to the calling thread, the thread that made the call to set thread token. But what Johnny noticed, and this is why it was cool, is he's like, wait a second, I can specify a handle to any thread, and it will cause that thread to impersonate the token that I'm specifying. And so he's like, what I do is I create a process. When I create that process, I get a handle to the primary thread of that process. And then post hoc, I can go in and tell it to impersonate. And so the big detection that he had for the create process with logon W, or with token W, sorry, was what he would do is, generally speaking, when people impersonate, you impersonate upward. And so you go from like admin to system, or you always impersonate somebody that has more privilege. Always might not be the right word, but generally speaking, that's the trend, right? You impersonate someone that has more privilege than you. And so the trick would be, you look for a child process who's running in a higher context, user context, than the parent. And that's like, why the hell is that happening? Well, it's because somebody did that explicitly, and that's how you would do it. Well, in this case, the child process is going to appear to be running as the same user as the parent, but the primary thread, which nobody has insight into threads. That's just like kind of how life is at this moment, right? Because threads are messy. Threads have numbers, they don't have names. And so they're really hard for humans to work with, because it's like, do you remember thread 1574 or whatever? It's like, no, nobody knows anything about that. And so basically he's like, I'm just going to impersonate on the thread, and then you're going to have a problem. Okay, so where was I? So we do the same thing, and now we have this. I felt really clever with this, so give me some credit. But see this thing? Does this look like a wolf or a fox? It looks like a fox, but it's a wolf. And so it's it's kind of like a mixture of the two, you know what I mean? And so that's where I actually literally Googled fox wolf or something like that. And that's what came up. It's called, I don't think it's a maned wolf. I think it's maned wolf, because it has this little tuft of hair on its back. When you put pictures of things in your slides, you of course have to look at their Wikipedia and read about them a little bit. But and it's not literally a mix between a fox and a wolf. It just appears to similar. It appears to be a mix. So what we end up with is kind of like a third or fourth species of token theft based on our analysis of the samples, right? And so just to bring it all home, if we were to look at all the function chains, we would see that there's some amount of variation. And then if we were to look at all the operation chains, we see that there's a lot of overlap. Does anybody see one operation that is consistent across all examples? Token duplicate, right? So token duplicate happens across all of them. The question is, do you have telemetry for that? And how much context is that going to give you, right? So maybe it gives you a lot, I don't know. And then our kind of final view of morphological view of these operation chains. And I did some purposeful spacing to kind of line things up so that you could see the similarities. So like we said, all of them have token duplicate. We see that there's similarities between the fox and the dogs on the early half of the chain, right? Actually, only the wolf is different in the early half of the chain, I suppose. But then what we see is that on the later half of the chain, the dogs and the wolves are similar, right? And the fox is just doing its own thing. And then the maned wolf or whatever is doing a little bit of a mix, it's doing a little bit of each. So then the question is we talked about, so there's all these questions that you have about, I didn't think I'd have time for this, but we got a little bit of time, so I can start talking about kind of what's going on here. So when you're building a detection, I find it valuable to start with one operational chain at a time and then add more and more. So like you would want to detect the dog sufficiently before you try to detect the dog and the wolf at the same time, right? Because it can only get harder, right, as you add more species. And so we talked about this idea of like, hey, which one is the optimal operation? We see operations, right, conceptually, but we can only see one at a time. And so which one would you choose? And I just like you kind of guessed, right? And like you were right. And that's great. And I think most of the time that will work, but there's actually like a logic. We talked about the different paths and all that kind of thing. There's this idea of necessity and sufficiency and logic. And so you could start to say, I have a goal and there are necessary conditions for meeting that goal, which means that in order to meet the goal, I must do this thing, right? So if you don't see X, then you know Y can't happen if X is necessary for Y, right? So it's like the absence of X means the absence of Y. That's the logical representation. But then you have sufficiency, which is if I see Y, then I can infer that X happened, right? And so the presence of Y indicates the presence of X. And so that means that this can only happen if this other thing has already happened. And so when you start to think about the best example I have is if we were to talk about credential dumping from LSASS. So imagine that the operation chain I don't have a picture of it, but we could draw it. Why not? Let's do that. So credential dumping from LSASS. Let's show what that might look like. Okay, so there's something like process enumerates, right? I have to enumerate processes. Then there's process open because I need to find I want to dump credentials from LSASS. And so I have a name for LSASS, but that's not the way that processes actually work. The way that it works is based on their process identifier. And so I have to enumerate all of the processes and then say which one of these processes has the name LSASS, right? So I enumerate, then I open a handle to LSASS, then I have to read, process read, sorry. I have to read the memory of LSASS. And then a lot of times what happens is that if you call that mini dump write dump function, you'll write a file. So there's like a file write, that's like the dump, right? And so this is an example to where just because it's later in the chain doesn't mean that it's better, right? Because you have to think about like, what are you trying to do, right? What you're trying to do is you're trying to read the memory of LSASS. And so that means that this is the optimal, right? The optimal operation. And so we start to think about it from a necessary and sufficient perspective, right? So what you could say is that in order to open a handle to LSASS, you have to first enumerate all of the processes. So enumerating processes is a necessary operation for opening a handle to the process. Then you could say, okay, well, in order to read, it's necessary to open. You have to open a handle to LSASS before you could read from LSASS, right? So that's necessary, right? And then, like, what you could say is that is file write necessary for actually reading the memory of LSASS? The answer is no, right? Like you could read the memory of LSASS and just hold the contents of memory in memory, right? And never write it to disk. That's what like Mimikatz does, for instance. But if I see a LSASS memory dump file, then I know that somebody read from LSASS, right? So I can infer that. And so the interesting conversation starts to get about this becomes both necessary and sufficient for the thing dumping credentials from LSASS. So what you would say is that this is necessary, this is necessary, this is necessary and sufficient, and this is just sufficient, right? And so that, like, for instance, no attacker is just opening a handle to a process just for the sake of like holding onto the handle and being like, look at me, I got the handle. They're using the handle for something, right? So it's not sufficient, but it's also, but it is necessary, right? And so the idea is that the necessary and sufficient operation is the intersection where you've minimized both types of error, right? So in detection theory is trying to solve, like trying to identify something in the face of uncertainty, right? And uncertainty means that there's error, right? Because sometimes you're going to be wrong. And there's two ways that you could be wrong. Sometimes you think you saw it when you didn't see it. Has anybody ever done like the auditory testing where they put you in like a silent room and you put on headphones? This is like a military thing. So I did it in the military a lot, but I don't know if normal people do it. So they put you in this silent room, right? And what they're doing there is they're trying to constrain the environment, right? So like your ability to discern signal in Times Square in New York City is going to be way worse than your ability to do it in a vacuum. And so if they're trying to only test your hearing and like maximize the range of your ability, they're going to put you in a room that's silent, right? And so they put you in a room that's silent. They put on headphones and then they play signals at different tones. And you have a clicker where you click the button every time you hear something. But inevitably, you're going to hear something when nothing happened, right? So there are situations to where the tone will play and you can't hear it. And that's like indicative of hearing loss, right? But then there's also times when you're like, you overthink it, right? And you're like, oh, was that something? Okay, let me click the button. And then they're like, yeah, you had like 5 misfires or whatever, where like there's no tone and you clicked it, right? So that's the example of the 2 types of error, right? So a false positive is when you click and there was no sound. A false negative is when you don't click and there was a sound, right? And like what you would say is that the tone that's playing that you're supposed to be hearing, that's signal, right? And then the hustle bustle of Times Square, that's noise. But there's 2 types of noise. There's external noise, which is Times Square, and then there's internal noise, which is sometimes you just think to yourself that you might have heard something, but other times, just in the random firings in your brain, the neurons that connect to tell you that you heard something may fire arbitrarily when there was no reason for them to fire, just like out of that just happens sometimes, right? And so that would be noise, internal noise. And so the idea is that you could have either type of error. Well, the interesting thing is that if you want to, let's say that process read is optimal, but you don't have telemetry on process read for whatever reason. The question is which way do you go, right? Do you go to sufficient or do you go to necessary? Now you go to necessary. You go to sufficient. Okay, yeah, it's opposite for me. Like I was like, which way is that? Anybody else have anybody disagree with sufficient? You can't answer because I've talked to you about this. All right, so the answer is it depends. And the thing it depends on is which one are you more sensitive to, false positives or false negatives? Okay, and so the idea is that if you're sensitive to false positives, you err in the direction of sufficient. And the reason for that is sufficient means that the thing already happened. But the problem with sufficient is just because the thing happened, that doesn't mean that the sufficient thing will happen, right? And so you have a higher propensity of false negatives if you err in the direction of sufficient. But if you err in the direction of necessary, right, you're going to have more false positives. The false positives are those paths that go somewhere else, right? But you're going to have no false negatives, right? Because you can't do the thing without doing this, right? And so the idea is that if you're sensitive to false negative, and that's a whole discussion about all kinds of things, right? About whether you should be more sensitive to one or the other. But generally speaking, every organization, in my opinion, should at least have some answer for which way would you rather err and under what circumstance. Like there's this thing called the Blackstone ratio in English common law. And so Blackstone was this guy who was a jurist back in England, way back in the day. And he said that when talking about the criminal justice system, he said, it's better that 10 guilty people go free than one innocent person be incarcerated, right? And so what he did is he established a ratio of their ability to accept false negatives compared to false positives, right? And so he said it's a false positive is 10 times worse than a false negative, right? And then Benjamin Franklin in the US, he said it's 100 times worse, right? So he I don't know, is that doubling down? Yeah, doubled down on it. and said it's a false positive is 100 times worse than a false negative, right? And so the idea is that the criminal justice system can't be right all the time, right? Because you simply just don't have the evidence all the time. And so if you're going to err in one direction, which way do you err? Well, let's say you could err in the direction of like, we're never going to convict somebody who's not guilty, right? The problem is there's a bunch of different ways that you could achieve that goal. One is you never convict anybody, and it's like, okay, problem solved. But then like, ideally, the entire purpose of the criminal justice system is that generally speaking, you want to be right most of the time, right? And so it's like, okay, well, how do we establish a threshold that allows us to obtain this, 100 to 1 ratio? Well, that's what beyond a reasonable doubt is, right? The idea is that you have to be beyond a reasonable doubt. You have to be guilty beyond a reasonable doubt in order to be convicted, is the theory anyway. And that's the standard. So the standard is extraordinarily high, right? In order to achieve that. If it was like a 1-to-1, then then you would have, there's a standard in US law, at least, that's the preponderance of evidence, right? Or I think it's called preponderance of evidence. So it's like a 51% standard. So it's like, it has to be more likely that you did it than not, right? And that would be if you had a 1-to-1 relationship between false positives and false negatives, you would use that standard instead of beyond a reasonable doubt. And so that's something that is worthwhile for people to start thinking about. It's like, which ones are worse, false negatives or false positives? I think logically speaking, false negatives have to be considered worse because the reason that everybody ever gives for why they don't like false positives is because it might create a false negative. And so it's like, if the reason why you don't like, anybody want to play a game, I guess? Okay, so you chose the sufficient, so I'm going to pick on you. So let's say that what do you think somebody would say if they were to say, I think false positives are worse than false negatives in the context of detection? Okay, so you're wasting time, right? Yeah, yeah. Yeah. Yeah, for sure. Okay, so I'm just trying to like walk the dog, which I guess goes with the theme of the thing. So so you said, oh, well, you have to look at all the alerts. That's the problem, right? And what is that like? You're wasting time is essentially the problem, or you get alert fatigue. Yep. And then you miss stuff. And what do you call it when you miss something that you should have caught? A false negative. Yeah. So nobody's ever answered that question differently. So I like, maybe there is a better explanation, but I've never heard it. So the idea is that false negatives, everybody, whether they accept it or not, thinks that false negatives in detection are worse than false positives. The problem is that the ratio of occurrence is like vastly disproportionate. So it's like you go 20 years and never see an actual, like, maybe not 20 years, but like you don't see bad things every day, right? But you could have millions of events that are legitimate, right? And so then the question is how much worse are false negatives and false positives? And it's like there's a threshold at which you become inundated and now you're not going to accept it. And so it's worth people thinking about that.
I think it's the user experience security organization.
Yeah.
What's the burden on this?
Yeah. See, like, I'm not a person that responds to alerts, so I like probably have like a little bit of like potentially unrealistic perspective, but I think of it like you could literally calculate your alert capacity, right? So it's like, let's say that alert handling capacity is like you could mathematically represent it as a function, right? So it's like number of employees, number of hours worked, number of alerts per hour. And like, obviously it depends on the alert and all that kind of stuff, but you could average it out or something like that, right? So you could say, let's say you have 10 employees. I don't know. I'm trying to think of how to make the number easy. 10 employees that work 8 hours a day, right? So that means you have 80 hours, right? And then they could do 10 alerts an hour. I don't know. So you have 800 alerts that you could process a day or something like that. So like as an organization, it's your best solution is to give people 800 alerts, right? You want to maximize your capacity. Otherwise, you're paying people to, you're wasting the time, right? Or wasting the capacity. Now, there are a better set of 800 alerts and a worse set of 800 alerts. And so like you want to maximize the efficiency of the alerts that you're giving people. But there seems to be a little bit of, there's a lot of people that will be like, oh, we want no alerts unless they're bad. And it's like, well, that the company, that's like not in the organization's best interest, right? Because if your standard is beyond a reasonable doubt for even alerting, right, then you're gonna not convict anybody. So like my analogy, going back to the beyond a reasonable doubt, is in the criminal justice system, you don't just like suspect somebody is doing something and then have to go to a jury and convince them that beyond a reasonable doubt, right? You do like, you have what they call like an escalating standard of evidence. So at first it's reasonable suspicion to stop somebody, right? And then it's probable cause to search them. And then it's, to indict them, it's like preponderance of evidence, right? And then it's, in order to convict them, it's beyond a reasonable doubt. And so the idea is that a lot of organizations are holding the beyond a reasonable doubt standard at the traffic stop level, as opposed to at the jury trial level. And so that's actually like, I don't know who saw Emilio and Remy's presentation, but one of the things, my interpretation of what they were saying essentially is stop treating the output of your detections like a jury trial and start treating it more like a traffic stop. That's my takeaway. I don't know if you like that analogy, put words in his mouth, but all right. So we got a couple more minutes, but okay. So here we have two chains. So we have two chains like the wrapper. But sometimes you just say stuff and stuff pops into your mind and you're like, okay, I got to get that out. Okay. So you have the first operation chain, which is like the first three samples basically. And then you have, so the dogs, and then you have the wolf, right? And so what you could do is when you're building your detection, you find what is the optimal thing. And then you would ask questions like, what telemetry do I have that would help me understand that a thread was set? Maybe like most EDRs aren't going to have that. And then you're like, okay, well, the next one is token duplicate, so on and so forth, right? But then you start to think, okay, well, what happens when I overlap these things? Well, in this case, when you overlap, the optimal operation is maintained. And so you're like, okay, that's a good match, right? So I can do a detection across both of these chains and I'm still using the optimal operation. But what about in this case? This is the fox, I think. Yeah, the dog and the fox. So if we overlap, now we have the early part of the chain, right? But notice that the optimal here is the thread set. The optimal here is the process creates. But then when we go and combine them, the optimal, so the idea is that in order for something to be optimal for a inter-chain detection, it has to be something that they both share, right? And so in this case, it's going to be token duplicate. But the problem is that token duplicate is neither the optimal for the first chain or the second chain. And as you go backwards, that means you get more false positives. So the combined detection for both of these chains it can only be as good as it can only be as, I don't know, I'm trying to think of how to say that. It will have at least as many false positives as either of the two chains or more, right? It can't be better. You can't get any better. And then you have a mid-chain overlap, which is something like this, which is also not great, right? And so you're going to have a similar situation to where the optimal detection in both cases isn't going to work. I didn't label. Did I label that? No. But yeah, so that's the idea is when you're trying to do multi-detection, right? So what you want to do is find something to where the optimal operations are going to overlap, and that's going to maximize your reduction of error, essentially, is what you're trying to do. Because there's this idea of like irreducible error, right? So when we start talking about, if we come back here, this is kind of the last thing that I'll touch on. When we come back here, I say that what I want to know, or like the thing that the attacker wants to do is read the memory of LSASS, right? But just because you read the memory of LSASS doesn't mean you're malicious, right? The problem is like, you could get even more specific. It's like, it's not just any reading of the memory of LSASS. It's like reading of the section of memory in LSASS where the credentials happen to be, right? That would be more accurate, right? That would reduce error even further. And then you could say like, oh, well, just because you read the section of memory where the credentials happen to be doesn't mean that you were intending to do anything bad with them. And so it's like, well, if I knew what they intended to do with it, then I could be even more accurate, right? And so, but there's a point at which your ability to gather more information ceases to exist, right? Like, I'm not going to get the attacker's intention unless I, have something that I personally don't have. So that there's some limitation to where you're kind of draw the rest of the owl, I guess, is maybe the thing. And that's kind of like irreducible error. There's going to be some amount of error that you're not going to be able to get rid of. But the question is, how do we get to the best starting point for something like what Remy and Emilio talked about, to where you now have indicators that you can use to kind of track things down a little further. That's not the slides. Okay. So let's see. That's it. That's all I got for everybody. Appreciate everybody's kind of giggles at my jokes and attention and answering questions, but happy to answer any like big picture questions or any specific questions over the next, I don't know. I think we got 15 more minutes scheduled for the time, or feel free to leave or whatever, but appreciate everybody's time. Yep. Thanks.
Yeah, well, I'm pretty sure you can get into the.
Yeah, thank you. Appreciate it.
I really like the interweaving of some of the processes and stuff like that.
I saw that you liked it. I could tell from your reaction. So
it's a little personal interest, but I really like the reference object oriented. Like,
oh yeah. Thank you. Yeah.
That's brilliant. I'm gonna use that.
Thank you. Yeah. The one of the things that really fascinates me. So I think in InfoSec, a lot of times we act like we have unique problems that nobody else has ever seen. And it's like, no. This problem's been solved by these people. And like, it's like,
yeah,
the medical field has been trying to figure out how to detect things for like ever. And like, it's literally life and death for them.
Yes.
And so they have a little bit more pressure to like actually answer that question properly. So
I love the idea of what you can do.
Thank you. Yep.